Okay, now you should see my presentation.
Yep.
Okay. Okay, so I will start now. Hi, hello to everybody. And for those who don't know me yet, I'm Aneta Wiśniewska. I'm working in Germany at the AIP. And I did my PhD on atmospheric seismology some time ago already. And I was using to that purpose ground-based measurements, which is kind of unusual. And therefore, I suggested the topic of discussion, how big progress we did in observations and what are the available data sets currently. Let's start at the point from we are starting right now. So what kind of data do we need for helioseismology? And well, it depends, right? It depends on the goal of our investigation. Do we want to do local or global helioseismology? What is our field of view? So maybe we will be interested more in a full disk. Sometimes it's also possible to do helioseismic analysis for the limited field of view. And maybe this is very controversial, but off-limb. Then it is also a question, and because I did atmospheric seismology, I know it's also important where in the atmosphere we are. So the location in the solar atmosphere. So do we want to probe photosphere, chromosphere, or maybe solar corona, which is now very, very popular topic, and a seismology of solar corona becomes very frequent topic of investigation. So then, do we want to have like one-dimensional or two-dimensional spectroscopy, or maybe imaging? And finally, if we want to probe, let's say chromosphere or solar corona, do we want to include also a spectropolarimetry? So not only spectroscopy, but also have some information about the magnetic field in these regions. So what kind of observations are possibly currently? This is the question. We are using mostly the space-borne telescope, right? The SDO data from HMI, then data coming from SOHO, MDI, and now the new instrument is the solar orbiter. So is it also possible to use ground-based observations? This is my next question. The answer is yes, although there is not so many instruments which can do such observations. And we have, for instance, in Europe, we have VTT, we had HellRide, Famulus maybe, and then Gong is like a worldwide, but I don't know why I put it in Europe. Then from the US telescopes, I know that we can use the data from BBSO. And the question is from where we can download this data. So basically, where is the helioseismic data available? So we have some kind of archives and websites like LIMSAL, JSOC, HelioViewer, of course, Gregor Archive, VSO, Solar Orbiter Archive. And in that point, if I forgot something, then please feel free to comment on it. Yeah, so this is the current state of the observations. So what is the progress? Do we need like different kind of data, like a totally different one, and which can help us to investigate even more, to help us answer the new questions which will appear? So we have then the KIST telescope. And if you have some ideas which instrument might be used on this telescope, I put the xerogenic near infrared spectropolarimeter as an example of the instrument which can be used for helioseismic probing. And we have also spaceborne telescope, which is newly launched, basically. So the solar orbiter, and to that we have specially designed instrument PHI, so polarimetric and helioseismic imager. And I think that some of you already mentioned that you would be interested in a observation of solar poles. So that would be the case of solar orbiter, I think, and it can provide even more data in a very, very good spatial resolution. And it also can do like a full disk measurement. So, but the problem is, what about the access to this data? So this is like suggestion for the discussion. So feel welcome to discuss. Yeah.
Thank you, Aneta. So what is kind of the status of Solar Orbiter right now?
Yeah, I mean, the PHI already starts the measurement. I am not an expert in that, but I'm interested, of course, to download this data. However, I've heard that they had problems with calibration, or maybe even with downloading, because, you know, maybe that solar orbiter is not always near to the Earth that we can download the data directly. We need to wait some time until it flies toward the Earth. So yeah, so I would be really, really highly interested to see those data. And I'm also interested whether you maybe know something about that, because the helioseismological community should be in particular interested to collect like a new kind of data.
I actually have some information on that. I was at a working group, I don't remember if it was earlier this week or last week, and they were talking about the PHI magnetic data. And they were saying that they are working on right now, they're producing the Carrington rotation maps, and they're close to being ready to make those publicly available. That should be in the next few months. But as far as the individual magnetic data, you're correct that there are some calibration issues that they're still trying to sort out with. And then once they get that all ironed out, I think there's a 3 or 6 month time period where they hold on to the data and they have it available internally before they will release it to the general public. So we're probably looking at closer to a year, I would say, before we're going to have those data available.
Okay, so very nice.
Irina had her hand up.
Yes, can you hear me?
Yep.
Okay, good. So I would like to just shed light on our modeling team activities. Actually, I developing a global solar activity data portal, which I hope it will see. We will have first light of we are going to release data. This product to community somewhere in summer next year, because what I learned actually it is a big pain to collect data in one place. And the reason why I start doing this because I have very hard time to find data what I'm needed for my research. It is kind of
Okay.
yeah, but also to address this issue, I should also mention in terms of helioseismological studies. Unfortunately, at least for right now, I don't have plan collect data to perform helioseismic analysis. But I am interested in collecting helioseismology data products, so already results. So But in a case if anybody need first anybody have data which is suitable for helioseismic analysis, I'm talking about simulations. This data can be made publicly available through NASA data portal. So we already have some examples of such data. So you're welcome. And if you have data products, I mean, which relate to global solar activity, I will be happy to host it. And of course, we will do like coordinate our work to make sure what your data kind of published in the right way with right description and right kind of credentials and everything. You can get a proper credit.
Okay, thank you.
Sasha?
Yeah, I think it's a very important issue to collect helioseismology data, and there are plenty of data. And recently I was looking at some data that was from Soha spacecraft, and now people don't remember that was like golf instrument is still working. Nobody's analyzing the data, and difficult to find this.
Maybe,
and
yeah.
also Virga instrument, and also they're still collecting data, you know, still it's, but nobody analyzing them, and nobody would even that looking at the data currently. And of course, you know, it will be very important to collect some old data, like with data, what at road did observations on some what was cycle, I don't know what, some previous solar cycles. It's very important from Mount Wilson, and BBS old data what Liebrecht Woodard, you know, they did observations, at least, you know, some the frequency tables would be good to collect and post somewhere. So it's really a very important issue, and to get, you know, access to the old data. And in terms of data access, you know, I don't know if it's Gregor data available somewhere. Generally, it's data from NASA missions. They, by definition, available immediately, but it's not the case for European missions. Like was, I forgot, was a French mission that observed solar radiance. I forgot the name. I don't think the data still. Yeah, I don't think it's still. Yeah, Picard. Yeah, I don't know if they're still available or not, because, you know, usually data and probably from solar orbit also will be available on the PIs of the instruments. I don't know if they make it available. But still, I think it's a very important issue to create a database, at least a website, and collect all the available data, because it's still like Virga Golf continuous observations. They're very important. And when we talk about the solar rotation, that now that it's important also to have low degree modes accurately measured. And say HMI, MDI, they don't provide such measurements. So it's, I agree that something that was probably that in our collaboration, that in COFFIES we should discuss this. Yeah, Todd said it on exabyte tapes, you know, and now it's very difficult to read this data, but whatever is available should be preserved somehow.
There's nothing difficult about reading the exabyte tapes. You just need to have a drive that works in a machine with a SCSI interface.
Silvana, I tried recently to read some exabyte tapes, you know, but I wasn't able to do this, you know, they have some limited lifetime.
You just have to go to a computer museum and then never mind.
No. Sasha is right. You know, some tapes don't age well.
Tapes don't age well, yes.
But Tim and Jesper have been in touch with me. We've been trying to revive reading the tapes, but it's tricky.
Yeah, so my comment was, yeah, the general data, like from HMI or from GONG, are of course available through their respective pipelines, like the JSOC, or from NSO GONG, you can also grab the data from there. So those kind of things are reasonably well available, but I think that it is, like Sasha said, the ones like the historic data, and I think Sylvain and you and Ed, you ingested some of the older stuff into the JSOC, right? I mean, so JSOC has been collecting some of the old data sets, but yeah, it's a problem then also to find somebody who knows how to process them, right? I mean, that it's not just, you have to collect the data, but you also need to collect the processing routines and the instructions that go with it. But yes, that would be a good thing to have. That's it.
Yeah, also, and yet, since you're in Europe, maybe you can advocate to make data available. Like recently, I learned that, say, data from Swedish Solar Telescope, you cannot get access to them. You have to purchase them. You see, so it's kind of all other data are free, but but not some. I don't know what about the Gregor data. I have not.
There is a
Sasha,
Gregor.
they need money to pay for the Russian gas.
Yeah, that's true. No, I mean, the data from the Gregor are partially, I would say, available, but only for some instruments, let's say for Greece. I think that this is not so good example for us, for the helioseismological community. We need like a more two-dimensional spectroscopy at least. So, and these from the old GFPI are so far not available, at least like a normal open access via website or something. So yeah.
Yes, I would like just first thank you first to Sasha reminding me about Golf and Virgo data, and I think it is really important data sets, and I really would like ask everybody for help. If you know about historical data which have a particular interest for global solar activity, I will love first just host it first to make sure we didn't lost it, and second we are going to look at data and think if we can improve in terms of identifying data gaps and I don't know, and regarding general discussion, I would like to add a problem if you would like, say, discuss about data storage, especially heliosmology data. In my vision, it is problem. It is not just grab data and keep it on tape, but question is about identifying data sets regarding different research domain. What I mean by this, so of course observers, people who doing heliosmology can correct me, but in my vision it is if we discuss about global heliosmology data and local heliosmology data, it is completely different data products. So it means treatment probably should be also different because we deal with different probably issues, and also data size of data and how we need to manage data to make access to this data more convenient.
Okay, Shay, then Roger, then Sasha.
Thanks, Nick. So I put this in the chat, but just to follow up on what Irina was saying. So again, COFFIES itself is not providing storage solutions at this point for data. But Irina, as Irina said, she's willing to host it and collect it, especially for the historical data sets. But what we are doing is we have what we're calling the COFFIES data portal, where we are trying to gather all of the various data sets or data products that are relevant to COFFIES and put them in one location where everyone can find them and have easier access to them, along with, for example, relevant references that should be cited for those data sets or products, or like the model results for ways, if, for example, your data set is actually, you can access it through JSOC, you can put the commands that you need to enter into JSOC in order to get that exact data set, that sort of thing. So we're trying to gather this stuff into one sort of data library, not the data itself, but links to the data and all of the relevant information so that it's easier for people to get to and access. And there's just kind of a one-stop shop for all of it. So in terms of EDS data, in terms of, the fee data, once it becomes available, all that stuff, If people can help get us that information to put onto the data portal, that would be really helpful for us, which would in turn then be helpful for all of you to be able to access it. So that was just my 2 cents that I wanted to put in.
Roger?
Yes, I just wanted to mention that the Mount Wilson system has been non-functional for quite a number of years now, I guess about a decade. The ways in which it broke are repairable. They cost money. There still is some on-site local expertise on what needs to be done to make the system work again. And of course, if we actually started taking data again, that would cost money to employ a couple of people to do the observations. And there'd be other expenses. It wouldn't be free. But I think the data has some unique features that it's really a shame not to continue into the present and future time. So the data could be compared to what was obtained back to 1967 at least. So I just wanted to throw that out there and find out if there's any sympathy for making an effort to do this. As I say, we still have some key people who are alive and well and able to help out with it. That won't last forever. So that is a factor to keep in consideration. So I just wanted to throw that out there.
Yeah. Sasha?
Yeah, I just wanted to say basically what Roger said, that it's very important for heliosmology. Most important is long time series. So the keys and all this, and also solar orbiters will provide some snapshots. But for heliosmology, we need really long time series, and particularly Mount Wilson, it would be, and important to keep some calibration. You see that because it's now we have problem of merging even MDI HMI data. Because of different calibration and for heliosmology. And it's very important now what we need to do something that to restore this historical Mount Wilson observations. They're not so expensive. And also I want to mention that it also that expertise in calibration of data is very important. It also being lost. It's not just like golf is collecting data, but the last time I calibrated by Thierry Apachot in 2017, they're now getting these daily feed files. And what to do for them, calibration is quite complicated, and Roger also is expert in calibration. So we need also, in addition to collecting data, to collect also some procedures and codes to process the data. I think this is something that for heliosmology team, maybe heliosmology team creates kind of a working group, and then collecting this, making the web page. At least that's to start with this.
Yeah, thank you.
Okay. Irina?
Yes, I would like mention a couple more points. First, it was a comment regarding JSOC. JSOC actually collects some historical data. I want to mention, at least for myself, it is really hard to get historical data from JSOC. And many links are broken, and it's kind of painful, and it will be good to have it kind of more friendly. And second is just, I believe, comment to share regarding data storage. Unfortunately, I'm not so rich person to host personally all data. Yes, I really think it's this problem to collect data and make them publicly available, or even make it initial processing of data to just for convenience to use is critically important. And what for right now I can do, I have agreement to develop this, but at some point, if it will reach certain threshold in terms of storage, we will need advocate NASA to purchase additional storage space and additional resources.
Yeah.
And,
The other.
my
Oh, go ahead. Sorry.
just almost done. So, and my idea is as soon as we will proceed with this task, collecting and releasing data to community, we can demonstrate to NASA what this product is really very valuable for community. And it will allow us to request more resources to support such activity. So, so it's not my kind of personal disk space.
Right. Yeah. Yeah. So, yeah. So we are asking everybody, but, you know, again, if you have something to go on the data portal, or you have you know, data that you want stored, especially if it's larger data sets, to use services like Zenodo or the Harvard Dataverse for now. We are in such preliminary discussions as to, I'm not even sure I should bring it up right now, but we are in some preliminary discussions about potentially making use of the Helio cloud for some like extremely large storage or data sets. So that's maybe in the pipeline, but again, it kind of depends on COFFIES members and people who want to use these data and who has what data and what needs to be stored and how big it is. So for now, again, we're asking people to use Zenodo and Harvard Dataverse and the like, and then again, send us your DOIs, that sort of thing, to include in the data portal. Again, because Irina can't host all of the data.
Dave, and then I think after Dave, if anyone else has any more comments, I would suggest we defer them to the open discussion portion a bit later, just so that we can kind of keep with the schedule. Go ahead, Dave.
Yeah, I just quickly say that we plan to make some modest accommodations to the JSOC on behalf of COFFIES. So Irina or anyone else, if you could ever send me a prioritized list of what would really benefit COFFIES, let me know and we'll try to make that accommodation.
Okay, thank you all. Should we move on to Jorn before Kyle? Would that make sense? Just due to the timing of everything. Thank you.
Yeah, I will be very short. That's just 2 slides.
Okay. Well, Anita only had 3.
The discussion is the problem.
Yeah. Well, it's not the problem, it's the point.
All
right.
Okay, so I hope you can see it. It's just a zoom. Okay, so I just want to show, I mean, it's not directly related to my work, but I think we discussed the mean field model or lambda effect model, how it's called before, and I just want to take 2 slides, what's it about and why it's actually very successful in reproducing differential rotation and the near-surface shear layer, and then also what's the problem with it. So to open some discussion. So the lambda effect theory goes basically back to Lebendinsky. That's why it's also lambda. So the L, so the Greek L is named after him. And so there's a famous book, here, this book, if you can see it, yeah, by Günther Rüdiger about differential rotation, where all these things are very well explained, and there's a series of papers dealing with this. So just to get everybody on the same page, so you normally start just by the mean angular momentum equation. What you see here is the omega, the rotation, and then you have the contribution from mirror circulation, for example, to transfer angular momentum, and the contribution of Reynolds stresses. And Reynolds stresses are basically the core of the lambda effect theory. So that's basically the correlation of fluctuating velocities and how the rotation basically acts on the convection. So it's driven by convection and rotation. And the idea of the lambda effect theory is to parameterize these Reynolds stresses. And what you do is now here I take two parts, which is important in this equation. You do it not just by a diffusive term, so that's the viscous diffusion, which goes with the gradient. So that's a very common known way to do it. But you have actually a productive term, which is proportional to the rotation rate. And this is basically called the lambda effect. That's why you have the symbols. And this arises actually from the anisotropy of the flows. And so, for example, near the surface of the sun, you have more radial flows than horizontal flows, and so on. And now you already see how things would play out when you generate the differential rotation. If you start with solid body rotation, this term will be 0 because it's only acting to the shear. So you need this term to produce in the beginning actually the differential rotation. And it goes on as long as basically these terms kicks in, and then you form basically a balance directly just through this equation. So that's of course more complicated than actually what I show here, but just to give you the general purpose. And the interesting thing is also recently you can, from this and from the theory, you can actually check observationally if these profiles of the Reynolds stress are basically in line with theory, because you can calculate. So this is just a you know omega, and this you can calculate these terms, and VT, I mean the turbulent diffusion must be a constant. So and then that's why you know basically what's the sign, how the sign of the Reynolds stresses varies with latitude. And if you would not, so and it will, if you would have only the last term, it will have a certain shape. But if you would add this term, it has a different shape. And actually, when you look at observations, for example, in this paper by Günther Rüdiger, he looked actually at the Reynolds stresses measured by Hathaway and Lisa, and found that this can be only explained when you add these terms, for example. So that's an interesting fact. So what is very common actually is then when you solve the whole thing, you of course solve also an equation for the mirror circulation, and your prescribe also how the turbulent heat flux is generated. But these models are actually very successful. So that's a more recent one, but there's also older ones, very successful in reproducing the differential rotation of the sun, including the near-surface shear layer. And so they're, in my view, at the moment, they're the only complete model who can actually reproduce the differential rotation. Complete, I mean that you can start with a solid body rotation. You have these equations, you solve them, and you end up with the solution, which is the solar differential rotation. And if you ask the people like Kichatinov or Günther Rüdiger, they will tell you there are no free parameters, because it's all based on a turbulence model. Of course, I would say there are some more free parameters, but relative, it's very self-consistent actually, this model. And when you now talk about the near-surface shear layer, they have a very easy idea why they actually get a quite good one. And that's again, you look at this equation, and then you apply what they call the near-surface shear layer condition. It means small Carois numbers, so high Rossby numbers, so very low influence of rotation on convection, and you have no external forces. So it means that this term is actually 0 because you don't have any flow at the, sorry, this term is at the, when you look at the boundary of the solar surface, so then you don't have strong outflow of upward flow, and then you can set this to 0 and then solve for this. And if you put in some terms, what is basically in here, you will end up by equation, or basically like this, that this radial gradient is around this V, and V is a certain parameter in their model, or basically a function. And if you put the numbers correct in and near the surface, you will actually get something which is -1. and is this also an outcome of the solution that is independent of latitude. And that's basically they're predicted earlier than the observation have found it. So that's actually a quite strong case. Yeah, also Rudi talked about this, that this was confirmed basically observation. But so yeah, that's very nice. But of course, there are lots of also problems with this. One is that it's actually, the theory is based on soccer. That means that is the second order correlation approximation. And this is normally working only for small Reynolds numbers. Or actually also for, yeah, doesn't matter. But so, and that's of course not true in the sun. So that's one thing. They never consider any magnetic effect. And I saw that Hideyuki is already in the audience, so he will of course strongly disagree. And what is not also included is the effect of banana cells, for example. So more like not super small turbulent motions, but like yeah, banana cells, which is relatively large scale convection. These effects are normally not considered. And often when you do run DNS, you can check different things that this doesn't really work with, it doesn't agree with the models, and especially that when you look at this theory, that seemed to work actually well near the equator when you do global models, or if you do different local models at different latitudes, but normally that fails actually at high latitudes. And that might be also related to that global simulations tend to get the near surface shear layer at low latitudes, but not really at high latitudes. So it's a very nice model, but probably it need to be refined to really work in the parameter regime of the sun. So that's just what I wanted to show you and open for discussion.
Thanks. I think Lauren has a comment or a question.
Yeah, I had a clarifying question and then like a real question. Just to clarify those coefficients, lambda and the turbulent viscosity, they're spatial constants. They don't vary with. They are normally so the it's actually more complicated. So the lambda is actually a series which depends on high orders of cosine and sine functions, and they all depend on your Chorus number or your Rossby number. Okay. So
at the end there will be R and theta dependent.
Okay. Well, I mean, that I think makes my second question more relevant, which is it essentially looks like you're
back from class. I'm in the lab.
fitting.
Okay, it's fine.
It looks like you're fitting the Reynolds stress.
Yuri, you need to mute.
Yes.
No,
it looks like you're fitting the Reynolds stress, which I have no problem with that. I just wondered, is there like a physical explanation for why the Reynolds stress would take that form? You've got one term proportional to omega, one term proportional to grad omega. Is there any reason why the background rotation should affect the Reynolds stress?
Yeah, there are some theoretical arguments, but the first actually argument came, or one of the first ideas came actually from observation, because you could do sunspot proper motions, and with this you can measure actually also the Reynolds stresses. And there you notice that this doesn't agree with this term. So having a contribution which is just bending on the shear, that's I think called the Boussinesque ansatz. This is a very old way of determining Reynolds stresses, but having this thing came basically from proper sunspot observation or sunspot motion observation, where you then see that this doesn't fit, and there's of course some theories to get this, but the also idea is that if you want to generate differential rotation from solid body rotation, you need to have a term which just depend on rotation.
and not just on the shear.
Sasha?
Yeah, I'd like to comment on your next slide if you can show it. So this is what first is it's actually this theory. It's self-consistent, so it's all separately equations for turbulences, you know. So it's and the free parameter is what is, as far as I know, it's mostly the anisotropy that was not, because it's you need to prescribe a model of turbulence. And the model of turbulence is based on mixing length theory. It's one of the problems because the scaling that what I prepared some slides on, if we have time for discussion, optimization shows that it's mixing length theory is not valid probably on the sun in terms of scaling.
That's another point. Yes,
so it's
right,
one of the problems, yeah. So then magnetic effects have been included, you know, what you say in our paper with Pippin, so it's for differential rotations. Then if you don't have banana cells, maybe it's a good thing because they've never been observed, banana cells. So then in terms of the DNS models are not really DNS, you know, that models with numerical viscosity. So they don't resolve turbulence to all the scales, you know, that needed for DNS, you know, never have DNS simulations for the sun because you can never resolve all scales, you know, you can have some
but you can
LES models, so you can have Reynolds averaging, but never DNS, you know, always, you know, end up with numerical viscosity. And that's probably the reason why it's, these terms are not reproduced and in lambda effect. And recently was interesting paper published, I think from an institute, Barikat and Capella, when they use the boxes like ARENA, but the boxes were simplified and they try to actually to measure lambda effect because it's not easy to separate in simulations. You cannot separate in observations. They try to, what they did, they suppressed in some test simulations horizontal velocities and then estimate the Reynolds traces and try to separate lambda effect from Reynolds traces. And but it's when you say it doesn't agree, it's not a problem with this mean field theory. It's a problem with the simulations.
Yeah, I mean, it depends a bit because you can do, of course, simplified DNS models, and you can actually bring there also the Reynolds number up. So there are some things which is not, I mean, there are some disagreements, especially in this paper here, which can we not just explain that you say we are not in the right turbulent regime yet. So you're right that when you do this global global convection simulation, it might be that you don't have a scale separation and these things, but you can do, when you do local box simulation, you can actually test this in more detail.
Well, one way to study, you know, the turbulence is to do real DNS, like, you know, fully spectral simulations, you know, locally fully resolved, you know, up to all scales, you know, that what like some say LES models were tested this way. And we still don't have, also for magnetic field, we don't have good LES model even. And what Irina was showing, it's basically LES, so it's still not DNS. And results, you know, they showed that some convergence in LES, you know, when you go to grid size of what 10 kilometers or so in, but near the surface. But still, it's turbulence is a big problem, you know. We don't understand the anisotropic turbulence.
Okay. Anyone else before we move on to Kyle Augustson's talk? All right. Well, thank you. Thank you all for the discussion. We'll move on, understanding that some of our friends may need to drop off before they collapse. So Kyle, if you want to share your screen, we'll move on to...
Take it away. Everybody see that okay?
Yep.
Okay, great. So some of you may know me from years past. I kind of took off and did worked on some other problems for the last almost 10 years or so since I've touched the sun. Some of those problems have involved fluid dynamics, and that's kind of what brings me back here, is looking at the MRI in global geometries. And in particular, we can look at stars, just like the sun. And one of the premises for that is this lovely long history that we have for the sunspot record, among other observations, of course. So this is just a compilation I did for my thesis in 2013, where I compiled all the possible sunspot results that were available in the literature at the time. Just because you get this lovely butterfly diagram that goes back almost 400 years, back to Galileo. So I joined a group in Northwestern that's been working on this problem and thinking about this problem for many years. So this is the Daedalus team, which is the code that we use. And a lot of these ideas originate with Jeff Fassel. And I've kind of been doing a lot of the heavy lifting and actually computing these things and working on a bit of the code. But some other people are involved as well. Keith Julian at CU and Nick Brummel loosely at UCSC. And we have some recent people who have joined this effort as well. So one is a grad student, Liam O'Connor, who's working on adjoint looping methods that will provide us a means of backing out what a good initial condition for our nonlinear simulations are, as well as a postdoc at CU, Bishik Manek, working with Ben Brown. So it's been 100 years since Maunder published his monthly notice paper with 40 years of sunspot data. And we have some theories about, of course, how these sunspots come about and how the global dynamo works. And a lot of that's happened in the interim. But we still don't have a very concrete one for why sunspots occur as they do and in the pattern that they do. And specifically in that they have this lovely equatorward propagation. And later on, of course, we found that there's a correlation with torsional oscillations. But alone, like this 1922 paper had 40 years of data. So that's already a lot of work to compile all of that, a lifetime of work. But we can go back to some other work as well, like this with simple observational rules, like those of Hale's law, just polarity reversals, Choi's law in terms of what the tilts are on sunspots. And we can also go back to some early ideas about the solar dynamo, like Babcock-Clayton models. And in particular, he had this interesting diagram in the 61 paper about how shallow is that dynamo. And a lot of the times, these people are thinking back to electrodynamics, where you can have like skin effects, plasmas and materials. And so he drew this very shallow connecting field line in the domain of the sun. Of course, they didn't actually know what the depth of the convection zone was at the time, like this. But the idea is like, we haven't had a lot of new observational rules that have come up in the last almost century. One place where this is, of course, changed is helioseismology. We have beautiful diagrams of what the internal shear looks like inside the sun. So this is work from Rachel Howe, her compilation and the Living Reviews of Solar Physics from '09. On the left, we have the differential rotation as a function of depth, or really the rotation as a function of depth, showing what we know is this, you have fast equator and slope poles. It also shows two of those shear regions that we are so fond of, the tachocline and the near surface shear layer. So what we're focusing on here, mostly because the shear in the tachocline is greater and therefore more prone to the MRI, is the near surface shear layer. So there was some work by Masada in 2011 where he looked at a JWKB model of the MRI, showing where it's most unstable to the MRI only, finding that you can get pretty fast growth rates in the shear layer because, of course, the shear there is strong. And as we heard this morning, Rudy was talking about this wonderful work from Antian Basu from earlier this year, where we can see on the right two different depths and correlations between logarithmic gradients in the shear with respect to time and latitude, and correlations with sunspots. And so what we see is that near the beginning of the cycle, of course, you have this at higher latitudes, you have a steeper gradient of the shear, whereas at depth you have a more shallow gradient. And as the cycle progresses, the amount of shear that you have moves progressively towards the equator. And we may have some ideas about how this can occur, kind of a clockwork method, but this is really, if this is the MRI, it would be a nonlinear process. And so far, we've really just been looking at linear things. So there was also work by Kagan and Wheeler in 2014, looking at growth rates that include things like buoyancy, which was not included in this previous plot here. This is just the MRI itself, where you can see that, of course, we have to compete with convection. And what that does exactly, we haven't looked into too much. We're really trying to look at simple problems first. And the simplest one that we wanted to do was what happens if you just have stratification and shear. But basically, this is what is our motivator. We have these wonderful time-dependent modes that look to be quite shallow. And so for this is our smoking gun, right? We have a link between a negative gradient and a time dependence, which sounds a lot to us like an MRI. So to remind everybody here, what is the MRI? So basically, it's an instability that arises from an attractive potential. So in this case, you have magnetic tension that binds two, let's say, elements in a disk or in a star. And if that gradient of angular momentum or rotation is negative, that means that this inner guy is rotating faster than the outer one. And what the magnetic field lines will try to do is pull them closer together. But in doing so, it transfers angular momentum to its outer partner, drawing energy from the differential rotation to do so. So for weak magnetic fields, namely low beta, this really, the growth rate here depends primarily on the shear strength and diffusion. And we can go back, at least for stars, back to the 60s or so, where they looked at this in terms of like Taylor-Couette flow. But for astrophysics, it really blossomed onto the scene again with Balbus and Hawley's work in the early 90s. And of course, there are many iterations of things. So what we're seeing here is a nonlinear simulation of a disk, particularly this figure 9 stuff, where you start with a poloidal magnetic field and a Keplerian differential rotation, namely, so for the sun, we were seeing that this d log omega d log r is like -1. Here it's -3/2. So it's slightly greater, but both can still be unstable to the MRI, as we'll see. But basically, you see this picture where the poloidal field here sets up an instability, and as it goes nonlinear, it starts to transport more and more angular momentum outwards, and this provides this means of getting material and disks towards their central object, whether that be a protostar or a black hole or some sort of compact object. So basically, the stability condition for this is that you have to have enough of a gradient to overcome what your magnetic field is and make sure that your scales are not too small. So I did mention Couette flow. So the biggest difference between these two things and why there was kind of a disconnect, I think, in the literature is that Couette flow sets up its own differential rotation. And a lot of the systems that are considered in astrophysics, you have some sort of differential rotation profile, like we have in the sun, for instance. That's a given, and it's maintained somehow. So to make a connection with more earthly things, there is some recent work from the Princeton MRI experiment, where they have shown that they can get an MRI, a saturated one. It took, almost 20 years or so to get to this result. This is a really specific kind of setup for a Taylor-Couette flow, where they've played a lot of games to minimize boundary layers, specifically here, and to have enough shear to actually trigger an MRI. And so what you're seeing on the right here are the solid dots here are ones where they have enough of a change in the magnetic field such that they consider it to be MRI unstable. And this is for a axis symmetric case. So as many things in Augustson-Hawley's work and earlier, a lot of the instabilities have been these interchange instabilities, which are axis symmetric. But of course, you can also have non-axis symmetric instabilities. And what we are considering so far are really axis symmetric cases. And of course, this comes along with some angular momentum transport. And so you can see that you get an outward angular momentum transport for those cases that they consider to be MRI unstable. So there's a critical threshold and negative Reynolds number in order for this to trigger. And that's something that we see also with our linear calculations, which I'll get to eventually. But as I mentioned, they also have non-axis symmetric instabilities, which is something that we'll have to consider in future work, specifically for the nonlinear MRI dynamos that I'll talk about in a little bit. So basically what they've been doing is they have a finite element code that can simulate not only the cylinder in itself, but its surrounding environment. So they can make contact with the observations that they make at the exterior of the experiment, which is through Hall probes. And what they find is the simulations agree pretty well with the amplitude of the modes that they get relative to the background magnetic field, seeing that they primarily get an n=1 instability. And what is curious is that most of these things lie below the linear stability diagrams for these things, which might mean that these are subcritical nonlinear instabilities, weakly nonlinear instabilities, which is quite curious and might have some bearing on the sun. We'll see. So to get on to what we've been doing, we're using the Daedalus code, which is a project over the last decade or so, to make it relatively easy to have spectral methods and multiple different kinds of geometries with relative ease for people to get into using the code, because you can basically type LaTeX type equations. You can play with a lot of different systems, whether they're 2D or 3D. You can have basically an arbitrary number of equations. So you can couple all sorts of different systems. You can have multiple domains that can be coupled, as like here. So you can couple between multiple codes as well. So here we have a coupling, for instance, between Athena and Daedalus. So you go from a finite volumes code to a spectral code. You can have multiphasic physics. Of course, we can do spheres as well, including the full ball. And it's relatively well parallelized and quick, so you can do fairly large simulations with it. But beyond that, you can do more than IVPs, these initial value problems. You can do eigenvalue problems or boundary value problems. And you can do local or global domains. And so in considering the MRI in the sun, what we've been doing is first looking at local instabilities. So an F-plane at the equator with just a pure vertical magnetic field, kind of the simplest configuration you can think of. This system has only a few parameters, namely, what is the strength of the shear, this S parameter here, how diffusive is the system, your Reynolds number, and then M is basically the ratio of your magnetic energy to your kinetic energy of the shear. So this is a well-known system, whether you want to consider it in cylindrical geometry or not. It fills in well with, it fits well with Augustson-Hawley's work. And what we find is that, so we can cover, with these Cartesian systems, we can cover a huge number of parameters, which is quite useful in filling out growth rate diagrams as a function of our input parameters. So what you're looking at here is a Boussin-esque system, so no stratification. There's, as you saw in here, there's no buoyancy, right? So there's no convection or anything. This is purely looking at what happens if you put in something that looks like a solar differential rotation, S, and fiddle with what is your Reynolds number and what is the ratio of your magnetic field to your shear velocity, shear kinetic energy. And in this case, basically what you see is you get a cutoff in either magnetic Reynolds number, if you want to call it that, or pure Reynolds number. Here we've just taken the magnetic Prandtl number to be 1. So what you're seeing is as you increase your Reynolds number up to 10 to the 7 in this case, the way we've non-dimensionalized things, you can get growth rates that are about 50% of the rotation time scale. And that occurs for relatively weak magnetic fields, as you expect for the MRI. In this case, the ratio of energies is 10 to the minus 5. What is also probably expected, if you're familiar with the local MRI instability, is that you're maximizing KZ, so whatever maximizes this growth rate here, KZ is along the direction of rotation and along the direction of the magnetic field, is that as you go towards higher Reynolds number, it becomes smaller and smaller scale. And what you're looking at here is actually the ratio between that maximizing KZ and the input depth of the shear layer that you're looking at, which we take to be just the outer 5% effectively of our domain, kind of mimicking the solar near surface shear layer. And what you're seeing on the far right are the radial structure for the highest Reynolds numbers eigenmodes as a function of the magnetization, of how strong the magnetic field is, as a function of depth. So for very low magnetizations, you have modes that are more localized near the lower boundary. And I should say also that to make contact with what the sun does, for instance, your magnetic field at, say, 1 Gauss at the surface corresponds to about 10 to the minus 5 here. So this would be weaker than what the average fields are on the sun. But if you go to stronger magnetizations, those modes move closer to the surface. But what you can see is that there's only a single node here. So the fastest growing modes are radially pretty mononodal, so they're more domain filling, whereas your maximizing KZ is many times that. So these modes are very anisotropic, which is kind of consistent with some of the nonlinear simulations I showed earlier from Balbus and Hawley.
Hey,
Now,
Kyle.
Yep.
Sorry, quick question. Can you just remind us what the orientation of the magnetic field is? Is it toroidal or?
This is purely vertical. So it's like
Okay.
it's colloidal in this case. You
And
can
that's
have toroidal field as
Right.
well. The instability is weaker in that case.
Okay.
But this has the rotation and the magnetic field aligned. And like I said, there's no buoyancy, so there's no gravity in this problem. But basically, this means you're taking a little box at the equator.
Okay. All right. Thank you.
Yep, no problem. Okay, so next we can throw in a bit more ingredients. We can have something that's a little bit more like the shear layer that's observed. So the previous one, of course, is a linear shear, so an okay approximation and easier to get a lot of analytical results from. But if we want to see what happens to the modes, if you add stratification, an exponential shear layer, and a dipole-like magnetic field, so allowing B to vary in radius in this F plane, it changes the growth rates, but moreover, it also makes the modes more isotropic in some ways. I should say more anisotropic. So the growth rates are larger in this Cartesian model for the same parameter values. And the growth
this is stable stratified, right?
This is adiabatic.
Okay.
Adiabatically stratified. But again, there's no buoyancy. We're just adding in a density to basically modify the Lorentz forces, so that they'll become more peaked near the surface effectively. So this domain is expanded a bit, so it goes down to 0.89 and to 0.99 here. So most of the shear is above 0.94, given the exponential profile here. So it basically drops from negligible shear at 0.94 to the solar-like shear near the surface. And so what this does is it confines the eigenmodes to the surface. This is actually a plotting error. This little bar here should be up near the top as well. But again, these modes are extremely anisotropic, with kz being much, kz over kx being much greater than 1. Okay, so I began saying that we wanted to look at what happens in global geometry. So the equations are quite similar. Again, we have some basic ingredients. So here's that exponential shear profile I was talking about. You can add in some basic approximations to the latitudinal shear. So our basic parameters are, again, Reynolds number, how strong your shear is, this alpha, which we take to be the average solar value, which makes it about, in units here, 0.033. And we have magnetization again. So this is assuming a dipolar magnetic field, which means that there's no current. So we don't worry about that term for this configuration. For other configurations, we do have to take that into account. Magnetic field configurations, we do have to take that into account. Okay, but how do we solve these things? So as you can see, like, this is a non-constant coefficient that involves latitude and radius. Okay, got a few minutes left. So that means that these equations are coupled in spectral methods in latitude and in radius. So it's a 2D problem. And so there's a couple of ways that you can approach this problem. We've tried several. The first is basically solving it as an initial value problem rather than an eigenvalue problem. And basically that means that you don't have to have huge 2D matrices that couple all of your coefficients properly. The negatives that we found were that the convergence is slow. Namely, you need to have an extremely high matrix power in order to get this to converge. So this means hundreds of thousands to millions of time steps. And in order to resolve these things, because as you also get with the Cartesian case, they're relatively small scale. It can be. And so that means that you're limited in the number of cases, like the amount of parameter space you can actually go and look at. So with this restriction in mind, this led us to approaching it in a different way. And this involved a lot of effort with the whole team here. And that was to implement matrices that can be coupled in Daedalus. So this means you can solve 2D eigenvalue problems in a sphere and in a few other geometries as well. These problems are a generalized eigenproblem. So it means that you have to use some specific methods in order to actually solve these. My job is basically implementing PETSI, so we can do these at a scale necessary to do some very high resolution studies. The algorithm that we use is a shift and invert algorithm, which means that you have to already pick a pretty good guess for the eigenvalue. And as you'll see, the Cartesian problem provides a decent guess. It's not exact, but it's close enough that it gets us a relatively sparse spacing between eigenvalues for the shift and invert algorithm, which means that it can converge relatively quickly. So how do you build something like this? Well, this is basically the machinery within Daedalus. So it uses something like a Galerkin method with taus for boundaries. So kind of a weak formulation where you pick a test function and integrate against them. And picking those test functions is very important as it determines the sparseness of your matrices. And so this is a lot of work for the sphere, work that Jeff and Daniel in particular were really leading, and that was implemented by Keaton into Daedalus. Okay, so we use these methods. It's about 100 times faster in wall time to compute these things compared to a power method. So we can run a much larger parameter space. It's computationally, it's in terms of the amount of compute hours that you need to do this, it's still about the same because you need to occupy a node with a large amount of memory to compute these. So it's very massively parallel, right? You can run all 10,000 cases in parallel, but you'll need 10,000 nodes to do it effectively. And it uses a pretty large amount of memory to do the LU decomposition necessary for the shift and invert method. But with that said, that means that we can get nice diagrams like this one, where you can directly compare what the Cartesian growth rate is for a given set of parameters to that of the sphere. You can see that they're similar, but not identical. Typically, the spherical growth rate is a little lower. meaning that the critical Reynolds number for this thing is shifted, but that the peak in terms of the magnetization is relatively similar. So what do these eigenmodes look like? So compared to what you might expect from the Cartesian analysis, right, you'd expect these to be really small scale modes where your vertical scale is much, much smaller than your radial scale. But in fact, what we find in all cases is that these modes maintain an aspect ratio of about 1. Now, so this is, you're looking at the full spherical geometry, the 3 components of the perturbed, so this is, again, a linear solve. So these are the eigenmodes of that big system that I showed you just a little bit ago for the set of parameters. So pretty high Reynolds number, 10 to the 6.5, and a relatively modest magnetization. So slightly off the peak growth rate, where the modes tend to be largest scale for this set of field configurations and differential rotation. So what you can see is that they're relatively, they're located at relatively low latitudes, again, for this field configuration. And the scale, the aspect ratio of these modes is kind of 1 to 1. Now, as you decrease the magnetization, much like with the Cartesian case, you get decreasingly small scales. But keep in mind that the aspect ratio is still really close to 1 for these modes. And you can also see why we need such high angular resolution for these. Not necessarily so high radial resolution, obviously, because they still have more or less just 1 node in the eigenfunction, or 2 nodes if you count boundary. But that the aspect ratio for these things still maintains about 1. And so now we're getting into some of the largest runs that I had done. So these require an Lmax, an angular degree of about 2048 to resolve this. And as you decrease the magnetization, it becomes increasingly equatorially confined and smaller scale. What we can also do is what we can ask ourselves, like, what's the effect of the boundary? So you can see that these are basically the outer 10%. This is with stratification and this exponential velocity profile and latitudinal differential rotation. If we look at a more modest Reynolds number and increase the domain depth, you can get an idea of how confined these things are to the outer 5% or so by radius. So this is the full 30% or so of the convection zone with the adiabatic stratification, meaning that the stratification has a density contrast of something like 300 or 400 between 0.89 and 0.99. Okay, one other thing that we can do, of course, is play with that magnetic field configuration. So if we instead take a confined dipole and confine that dipole to the outer 10% by radius, we can greatly extend the extent of this linear instability. And basically what we've started to do is to take some of these most unstable eigenmodes and look at their nonlinear evolution. So you can see this is one of those equatorially confined modes, not one of these larger scale modes. And we plow it along for 40 time units. And let me show that movie. I'm almost done. So what you can see is a kind of an alphanic response initially, and this is seeded with small scale noise. And over these 40 rotations or so, you develop a larger scale, oh, come on. In M structure as we get towards the end of this thing. Stop it there. Nope. Come on. So, oh, dang it, it's still playing it. Pause. Anyway, so the point is that if we can evolve this thing longer, so this one is just kind of a short evolution, we need to evolve these things over diffusion times. And if we can do so, we're curious what the saturated state of this looks like. This is for a set of parameters where we think we'll have at least a stable dynamo. But this is yet to be seen. So I'm just going to skip over this in the interest of time since I'm already a few minutes over. So basically, we can trigger both local and global MRI with solar-like parameters for the differential rotation. Of course, these Reynolds numbers are far lower than the sun, but at the same time, we can maybe ask, what does convection do in terms of turbulent Prandtl number or turbulent Reynolds numbers? Low latitudes are preferred, at least for our dipolar magnetic field. This shear sets the product of in the MRI sets the product of what B and K can be for a fixed rho. And like I've just shown, we have some studies of the nonlinear state that are actively underway. But basically, we have global and local MRI, at least in the linear problem. The question can be, how can this interact with convection? So this is one thing that we'll look at eventually. Maybe, given this, some of the things that we've seen this morning, one possible scenario is that the MRI transports angular momentum outwards, decreasing the shear. So if we go back to Rudy's stuff this morning, you have an increase in the steepness of the shear when magnetic when sunspots start to form, and you get a positive correlation between this NSSL changes and sunspot formation. So maybe what happens is it steepens enough, you trigger an MRI, feedback lessens this gradient as the cycle proceeds, and somehow it moves towards the equator. But how this is actually globally maintained, well, that's the question of this whole workshop. Is it Reynolds stresses? Is it thermal wind? But basically, the MRI is an interesting thing. The shear is strong enough to trigger it, at least in the linear, in this simple problem that we're looking at. And we're really curious to see how this interacts with buoyancy and convection. Now I'll just stop there.
Great, thank you, Kyle. We'll take questions. I see Gustavo has his hand up, and then Sasha.
Yeah, thank you. That's quite interesting. So in your equations, do you have dissipative terms or this? No, I don't think so.
So there's no thermal energy equation in this, not yet.
Right.
But there is diffusion.
Viscosity, you mean, or?
That's right. There's a physical viscosity that we put in. That's the inverse of the Reynolds number.
What value are you using for this viscosity?
Well, it depends on, like I said, the Reynolds number that we choose for these. So it tends to be like 10 to the minus 6. So nu is something.
So like you're tending towards molecular viscosity in that case, right? Or trying to have molecular values.
Well, given the way we've non-dimensionalized the problem, probably not. We're still probably 6 orders of magnitude away or something. Just like if you're running a convection model.
But it's not the order of magnitude of turbulent convection, which you can perhaps try, and you can see if this is wiped out. So that's a way to check if convection what convection
that's a good point. That's a good point. Yeah. Does it shift the Reynolds number to below the critical threshold?
Correct.
And then we get back to the experiment that I was showing that, well, it too is also unstable, at least non-linearly, even below, with magnetic Reynolds numbers below the critical threshold. So this could be something like a subcritical nonlinear phenomenon. But like I said, we've only just begun the nonlinear experiments.
Okay. Yeah.
We'll see.
Yeah. Thanks. That's quite nice.
There's another question.
Yeah, I have a question. Thanks for a very interesting presentation. It's really interesting. A quick question about your criterion stability. It looks like you have a wave number K in the right-hand side, but your simulations show that high K is mostly unstable. So why don't you see instability for low K?
B is low, right, in these. So there's a maximum magnetic field that you can have.
But still, you know, for K is, you know, it's product with B, right? So for even for low, when both values are low, then it's more unstable, right? Or misunderstood something in your last slide was.
That's so. It's. Can you see the screen now still?
No.
Oh, okay. Let me reshare it then. Sorry. Yeah. So this criterion here.
Right. Yeah.
So if B is low enough relative to our shear.
Right. Yeah. So that's the stability condition. I see. So instability is reverse, right? Okay. Okay. Usually they show instability and then okay. But I have also a comment about this. So it's you know, it's really important to. It's been discussed some time, you know, long ago that Rudiger discussed this also in implication to the sun. But the question is if the instability can survive turbulent convection. You know, that was one of the problems.
And this also was Gustavo's point as well, right?
Right. Yeah. It's and then when you reduce effective, you know, magnetic Reynolds number, then yeah, it will not be unstable. But also, what's interesting that in our dynamo team that we discuss also kind of magnetic rotation instabilities, but not of this type, instability of toroidal field in the tachocline, because the problem is that Peter Gilman, also Dick Patty, they, you know, them. They develop these models, and one of the problems is to how we explain latitudinal distribution of, you know, to most on large scale. And in fact, when you substitute your, and it's mostly kind of similar to Rossby waves. Rossby waves, they become unstable in differential rotation. And I wonder if you turn off magnetic field completely, then with the solar differential rotation, it's unstable. It's actually unstable with respect to excitation of Rossby waves.
So
you should be able to see.
Right. So at least
to see excitation of Rossby waves even without magnetic field.
Right. So at least
it would be interesting to check this. And also in terms of the buoyancy, and buoyancy is also important even in the convection zone. This n squared is negative and small, but it's still ratio of n squared to omega squared. It's still large enough. And in fact, buoyancy will help you to solve equations because it will restrict vertical motions. Yeah, so then then you can separate these, and then even in your equations, I did this without magnetic field. You can do decomposition into some eigenfunctions with a eigen problem. Usually you have spherical harmonics, but in case of rotation, the basis is what's called Laplace tidal equation. Exactly. Yeah. So actually, buoyancy will help you to solve this problem, and would be more relevant to applications.
For sure, yeah. So that's the next step, right? We'll add that in.
Yeah, I'm very curious to see you feel the results. Yeah, thank you.
Yeah, we just wanted to see, can we get an MRI with solar-like parameters?
Right. Yeah. No, it's very interesting experiment. Yeah, it's no doubt. Yeah. Thank you.
More of a fluid experiment.
Okay. Well, thank you, Kyle. Very nice talk. I think in the interest of time, we will move on to Hideyuki, who will be talking to us about simulations of the convection zone, including the near surface shear layer. And then we'll move on to some more open discussions after his presentation.
Okay. At first, I have a very heavy movie in my slide. And I don't think that it does work via Zoom. So if you are interested, please download from the chat link. Okay, this is a 6 minutes long movie, so I don't play full thing in the presentation. Anyway, so thank you for giving me an opportunity to have a talk here. So I'm Hideyuki Hotta from Chiba University, Japan. So today I talk about our new very large calculation for the reproduction of the first equator, a near surface shear layer, and the poleward linear flow. Okay, so at first I want to focus on our recent finding of the first equator, and then so I quickly explain our new finding, and then I then go to the near surface shear layer stuff. So maybe I can skip this slide. So we have the observational result of the differential rotation and the meridian flow, and there's a fast. So in this study, in this presentation, I addressed only the fast equator and the conical profile and the near surface shear layer and the poleward meridian flow. Okay, Anyway, so I want to go to the convective conundrum. So this is the observational result of the differential rotation, and this is a very confirmed result. But recently we had a problem. This is called the convective conundrum, and there are a lot of things in the convective conundrum, but I focus on the differential rotation aspect. So the problem of the convective conundrum in the differential rotation aspect is when we increase the resolution. So we believe that this is approach to the reality, and there is a problem. So this is a one typical result of the high resolution simulation. And then when we do a high resolution simulation, so we tend to have the fast pole and a slow equator. And this is a Rossby number problem. So this is a Rossby number. So Rossby number is the velocity and the rotational rate and the spatial scale. And we need to suppress decrease the Rossby number. So I mean the increase the rotational influence to obtain the fast equator. This is a problem. So anyway, so we always want to have a small Rossby number. So I don't explain the detail, but there are a lot of ways. So increase angular velocity and decrease luminosity, or increase viscosity and thermal conductivity to obtain the small Rossby number. But recently we find that so when we increase the resolution very, very large, very, very high, then we can obtain the fast equator. So even without assuming these things, these ad hoc things. So this is a low resolution calculation, and in low resolution calculation, so we have the fast pole. And when we go to this resolution, this is something a 5 billion grid point for the solar convection zone, and we can obtain the fast equator. So this is published in Nature Astronomy last year, but this is not the main topic of this presentation. But this is very important also for the near surface area. So there are important points in our new calculation is regime. So we call it HK regime because this is a paper of the Hotta and Kusano. And we find that so the magnetic field is dominant in the convection zone in the high resolution calculation. The horizontal axis shows that here shows the radius. Here is the base of the convection zone, the top boundary, and the solid line shows the root mean square magnetic field strength, and the dotted line shows the equipartition magnetic field strength, or something like that. So you can think that the root mean square is proportional to the square root of the magnetic energy, and the equipartition is proportional to the square root of the kinetic energy. So when the solid line exceeds the dotted line, this means the magnetic energy is larger than the kinetic energy. So in typical calculation with the solar parameter, we typically obtain the smaller magnetic energy than the kinetic energy. Of course, when we increase the rotation rates, magnetic energy easily exceeds the kinetic energy. But this is a solar case. So this is this blue line is a low resolution case. In the low resolution case, the solid line is always smaller than the kinetic energy. But when we go to the high resolution, so high resolution is green, and this is equipartition magnetic field, and this is represent. So this shows the kinetic energy, and this solid line is the magnetic root mean square magnetic field, and it is clear that we have the super equipartition magnetic field in the dynamo calculation. So this is very important. So in our high resolution calculation, magnetic field is dominant in the convection zone. So we call it the HK regime. So due to that, the magnetic and angular momentum transport is very important in our calculation. So this shows this value. So this is the angular momentum transport by the Maxwell stress. And this transports the angular momentum radially outward. So this causes meridional flow. So clockwise and anti-clockwise and clockwise double cell meridional flow in the convection zone. And this can accelerate the equator. So this is a very complicated story. So, but I can review the all the story of our high resolution calculation. But this is very long story. So the super equipartition magnetic field can be generated by the compression, and this can transpose the angular momentum radially outward. Now this can cause meridian flow, and the combination of the magnetic field and the meridian flow can generate a fast equator. But so typically it takes 3 hours in the seminar to explain whole story. So if you are interested, please see this paper or invite me to your group seminar. So I had 10 times. I have a seminar of this topic 10 times, and I'm used to talk about this thing, and I'm very glad to. I'm very happy to talk about it. So, but if you are interested, invite me. But this is not main topic. Important point is magnetic field is really important for the angular momentum transport. Okay, so before going to the main topic, so I want to make it clear. So sometimes I was asked, so sometimes people have the common misconception. So the people think that we can reproduce the fast equator because we can reproduce low Rossby number. So I mean the strong rotational influence. This is a misconception. So actually, so we analyze our data very we analyze our data, and we found that so in our high resolution calculation, so the convection is in the high Rossby number regime. So the rotational influence is very weak in the high resolution simulation. Actually, so the root mean square velocity is suppressed by the magnetic field, but the high resolution effects increase the Rossby number. So this is not correct understanding. The correct understanding is magnetic field transpose angular momentum for the fast equator, and the convection stays in the high Rossby number regime due to the high resolution. So the more radial, so more negative radial angular momentum transport is achieved in high resolution. So anyway, so the important point in this calculation is that we stay in the high Rossby number, I mean the weak rotational influences. Okay. Finally, so we can go to the main topic of the near surface shear area. This is our differential rotation and the meridian flow. And we can reproduce the fast equator in our calculation. But a near surface shear area is very weak and almost nothing. And in addition, so there is red color. So this is the meridian flow and the V theta. And we can see some poleward flow, but this is too weak. And we can see some equator ward flow in the thin layer. So this is clear, but so the top boundary is located as a 0.96 solar radius, and we don't include the near surface layer. So maybe we cannot reproduce a near surface shear layer and a poleward flow. But near surface shear NSSL is difficult. So the convection in the near surface shear layer has a very small spatial and a time scale, and which makes the calculation very difficult. So we need to cover the very broad range of the time and space in one calculation. So this is due to the sudden decrease in density and the temperature in the near surface layer. So this is an observational result, and we tried once to reproduce a near surface shear area, and we argue that we can reproduce some fraction of the near surface area in our 2015 paper. This is my PhD work. And at that time, so we haven't solved the convective turnaround and the differential rotation aspect. So we need to decrease luminosity to reproduce a solar-like differential rotation, because we needed the strong influence of the rotation. So we need to decrease the luminosity. And we can see some evidence of the near surface area. But as everybody says, so we cannot reproduce near surface area in this layer, so mid-latitudes. And Ron Matejewski also did some very nice calculation, and he increased the rotation rate 3 times. And he can also reproduce the near surface shear layer in this latitude, but also in the mid latitude, they cannot reproduce it. And why? So it is said that so I will explain in the next slide. And the approach is still rotationally unconstrained even in the near surface shear layer. So we cannot reproduce near surface area in the mid latitude. So this is there is a very nice study by the Gustavo in the 2013. So the problem is that we cannot reproduce the near surface area in the mid latitude. So anyway, but we can see something in this layer. So this is a suggested mechanism in our paper. So one important aspect of the near surface area is how to maintain the non-Taylor Proudman state. So typically in the tachocline and in the mid convection zone, the Baronic terms and the entropy gradient is an important term to maintain the non-Taylor Proudman state. But we argue that the advection is very important in the near surface area. So the mechanism is very complicated. So I try to explain it. So near surface area has a negative d omega dz. So this means that this want to create a negative vorticity in the northern hemisphere like this. So there is a Coriolis force. And so we need a force to balance with this Coriolis force. So one can be the buoyancy. So one possibility is a buoyancy. So the other is a advection force. So our suggested mechanism is rotationally unconstrained convection can transpose the angular momentum radially inward, and this can cause meridian flow, right, with this vorticity. And there is a very small scale turbulence in the near surface shear layer. And so this can act as a turbulent viscosity. And the turbulent viscosity force on this sheared meridian flow can be like this. And this can be balanced with the Coriolis force in the near surface shear layer. So this is our suggested mechanism. But there is a dilemma. Suggested by Matilski in 2019. So anyway, so it seems that we need the rotationally unconstrained convection in the near surface shear layer to act like this. But they found that the downflow is typically faster than the upflow, can be rotationally unconstrained in the near surface shear layer. But upflow is rotationally constrained in their study, also in my calculation. So this is a very nice figure in the Matilski 2019. And the horizontal axis is the radius. And I guess this is the base of the convection zone, the top boundary. And this shows a radial angular momentum flux. If the radial angular momentum flux is negative, this indicates the flow is rotationally unconstrained. So I think this is downflow. So downflow is a negative. So this means the downflow is rotationally unconstrained. This is very good for the near surface area. But the upflow is broad and slow. And the upflow is still rotationally constrained. So there is a dilemma. So we needed the rotationally constrained convection for the fast equator. So so banana cell can transpose the angular momentum radially outward, and this can accelerate the equator. But at the same time, we need the rotationally unconstrained convection for the near surface area. And we thought that the variation of the Rossby number on the radius can cause the smooth transition from this to this. But it seems that the transition, smooth transition is very difficult. So we cannot reproduce the near surface area with the fast equator. So this is their understanding, I guess. And as I explained, so in HK regime, so we don't need the rotationally constrained convection because the magnetic field can transpose the angular momentum radially outward. So how is the near surface shear layer in our high resolution calculation? So this is a purpose of our study. So to investigate the near surface effect in the HK regime. So how is the near surface shear layer in the poleward flow in the HK regime? But as I explained, the including a near surface is really difficult in the global convection calculation. So we need to increase resolution, increase the number of the time step. So this is our Nature Astronomy paper. This is something 5 billion grid point calculation, and then we increase the resolution to the 12 billion grid point calculation. And the top boundary is previously the 0.96, and then we move to the 0.99. And this caused a large number of time steps. So this one was 3.5 million, but a new simulation is 12 million. So the numerical cost in the numerical number of grid is 2.4 times, and the number of time step is around 4 times. So the new calculation is around 10 times larger than our last year calculation. Anyway, so this is the result, and so yeah. So initially, this is polar region is rotating faster, but maybe we can go to the final bus. Okay, something like that. But if you are interested, please download the movie. Okay, so the most important slide is this one. So this is the differential rotation and the meridional flow. And we can nicely reproduce the fast equator and a near surface shear layer, even in the mid latitudes. And also in the meridional flow, we can reproduce a very nice meridional flow. This will be compared with the observation in the final part of the presentation. Okay, so I think so. This is the best model, current best model in the global convection calculation to reproduce meridional flow and near surface shear layer. So from here, we discuss physical mechanism for maintaining the near surface shear layer and the poleward meridional flow in the rest of my talk. Okay, before going to the actual mechanism, so I'd like to address the velocity and the magnetic field, the general feature. So I also shows this is our last year paper and the high resolution calculation and this study. And the horizontal axis is the radius, vertical axis is the root mean square velocity. And the root mean square velocity in the convection zone is almost identical to the previous calculation. But we have the near surface layer. Near surface layer has a very fast convection velocity. And this also shows a magnetic field, and the horizontal axis is the radius. And so this orange line is solid line is the root mean square magnetic field strength, and this dashed line is the equipartial magnetic field. And in the convection zone, the result is almost identical to our previous calculation. But the important point is here. So in the convection zone, magnetic energy is always larger than the kinetic energy. But on the near surface layer, kinetic energy is larger than the magnetic energy. So we found that this transition is very important for the near surface shear layer. Okay, please remember this feature. Okay, at first, let's go to the maintenance mechanism of the meridional flow. So in order to understand that, we need to see the angular momentum conservation law. Sometimes this is called gyroscopic pumping. So when we exclude, anyway, so this is the angular momentum conservation law. So there is a 3 contribution in the angular momentum transfer. One is the meridional flow, and there are turbulence, Reynolds stress, and there are Lorentz force, and this is a Maxwell stress. And these should be balanced in the statistically steady state. So I put all the thing in this figure, and this is a meridional flow contribution and the turbulence and the magnetic field. And the important point is turbulence. So meridional flow want to increase the angular momentum in this layer. So turbulence want to decrease the angular momentum. So due to the radially inward angular momentum transport in the by the high Rossby number regime. So this, I mean that the poleward meridional flow can be generated by the turbulence, because in the near surface area, turbulence is important, because I show you. So the turbulence is larger than the kinetic magnetic energy, and the reason for the poleward meridional flow is the turbulence. Magnetic energy, magnetic field is very important in the convection zone, but weak in the near surface area. So the turbulence is the reason why we have the poleward meridional flow. Okay, so there's a competition between velocity and the magnetic field. In the convection zone, the magnetic field wins. So the magnetic field transports the angular momentum radially outward. This is a reason for the first equator. But in the near surface layer, turbulence wins. So the turbulence transports the angular momentum radially inward. And this causes the poleward meridional flow. And the dominance of the flow in the near surface layer is the key for the poleward meridional flow. Okay, next is the generation mechanism of the near surface layer. And so this is a longitudinal vorticity equation. There are a lot of contribution. One is the Coriolis force and the advection and the volcanic term. So in previous work, so my PhD work, I discussed only these things. But I also include the magnetic field in our analysis. So this is the result. Horizontal axis is radius, and I average these values latitudinally. And so this green line is the Coriolis force contribution, this one. So in the convection zone, this blue line has a responsibility to maintain. So this is a barochronic term. Barochronic term is almost identical to the Coriolis force. But in the near surface layer, the barochronic term decreases. I even go to the negative contribution. So the one dominant contribution is this magenta line. Magenta line is a magnetic field. So the magnetic field can maintain the near surface area. Of course, there are some contribution for the orange line. Orange line is the advection. So this acts as a turbulent viscosity. But anyway, so the dominant contribution is a magnetic field. Okay, so reason why we have the dominant contribution from the magnetic field can be explained like this. This is magnetic field, Maxwell stress, and this can maintain the near surface layer. And so there's a correlation between BR and B theta. So generating a BR and B theta, so in order to generate a BR and B theta, so there are two possibilities. So one possibility, so the shear of the flow. And when there is a shear, and this can correlate the BR and the B theta. And I see the two shear. So one is a meridional flow shear, both are meridional flow shear. And it is clear that this negative shear can generate this positive value of the this Maxwell stress. And we can say that, so there is a shear of the meridional flow. And of course, there is a magnetic field. And the shear stretches a turbulent magnetic field. And the magnetic field acts as a magnetic tension. And this can be good force for this one. And this magnetic tension can balance with the Coriolis force in my calculation. Okay, so this is a summary of the mechanism for the near surface shear layer. And the turbulence transports the angular momentum in the near surface radially inward. This can cause a sheared meridional flow in the near surface shear layer. And there is a turbulence, and this sheared meridional flow can generate the BRB theta negative, and this can be magnetic tension like this. This can be balanced with the Coriolis force in the near surface shear layer. So the difference from our previous mechanism. So sheared meridional flow has an important role on the near surface shear in both studies. So that I'm happy. So even my new calculation does not ruin my PhD work. But we suggest that the turbulent viscosity is most important term. But we found that magnetic tension is more important in higher resolution and including a magnetic field. And the difference as a new calculation stands in the HK regime, in which the destructive banana cell is not required for the, so destructive for the near surface shear layer is not required for the first equator. And the Coriolis force is balanced with the magnetic tension. So interesting point is actually in the even in the near surface shear layer, magnetic energy is smaller than the kinetic energy. But the magnetic tension is more effective than the turbulent viscosity. So the magnetic tension is effective in the near surface shear layer. So I also show the, so we obtain the meridional flow, and this can be compared with the observation. So the actually, so observation for the meridional flow is very, very difficult, but we can directly compare our calculation with using the travel time with the helioseismic data. So I download the Gizon 2020 travel time data, and horizontal axis distance, distance, and this roughly corresponds to the near surface layer and the deep layer. And actually, so our calculation, the top boundary is 0.99. So we need to assume the flow in the real surface layer. And the surface layer is something like that. So we just roughly assume. And we put the 3 parameter and the 3 parameter range for the near surface meridional flow. And we calculate our travel time, and this is a 3 travel time, but all the thing is very consistent with Gizon's travel time difference. So we can say that, so we cannot rule out our resolution, our calculation result, even with compared with the local helioseismology. Okay, so this is a summary. So we carried out a new simulation with a larger domain and a higher resolution. This is 10 times larger costs. And the first equator and the near surface array and the poleward meridional flow are simultaneously reproduced. The mechanism, the poleward meridional flow is generated by the turbulence, and the near surface array is generated by, maintained by the magnetic field. And the interesting interaction between flow, magnetic field, and the perturbation mean flow is important. So, and our paper and the Matitsky paper requires a small Rossby number for the first equator, which reaches the banana cell and destroys the near surface layer in the mid-latitude. But in the HK regime, the magnetic field can transpose the angular momentum and Rossby number, and the Rossby number does not have to be small. Okay, that's it.
Great. Well, thank you very much, Hideyuki, and thank you for joining us so early, your time. I see Gustavo had his hand up first, so Gustavo, you have a question or a comment?
Hi, thank you, Hideyuki. Very nice talk. Yeah, I have a question regarding your slide number 19. If you can go. Oh, okay. This is vorticity production. Because normally the baroclinic term balances with the Coriolis force term. So normally they have opposite signs. So why here do you have? So it means that there is no thermal wind balance in the convection zone.
So this is the negative sign of the Coriolis term. So if this is the green line and the blue line is the same, this means the baroclinic term is balanced with Coriolis force in the deep convection zone.
So you have the opposite sign already.
In the near surface layer.
Right? No, in the convection zone, I mean.
In the convection zone, so this is a P bar is balanced with the P core. Okay. So this is a negative sign of the P Coriolis force. So if this is identical to, so typically, so this term is in right side, right hand side. So, but I move it to the left hand side. So if blue line and the green line is identical, this means okay.
But in general, to the balance, then you should have this term negative, right? And you should have as a zero balance. And but in that case, then you will have this P bar having very positive signs close to the surface too.
Yeah. So yeah, so this should
so
be
what
negative.
is balancing the what is doing the meridional balance in the close to the surface?
So in the meridional balance is in the barochronic term has a negative effect. This barochronic term want to destroy the near surface shear layer, and the magnetic field want to maintain the near surface layer. So this is a magnetic field. Okay.
Okay, and another question: how do you compute the travel times for the last slide that you presented?
Okay, so I use an array approximation. So
okay.
Okay.
Yeah, I have a question. Can you get back to the slide where you show the divergence of your Reynolds stress and of your Maxwell stress? Maybe it was 18 or 17. There we go. Yeah, so this is very interesting to me because the magnetic contribution looks almost exactly like what you would expect the hydrodynamic contribution to look like in a low Rossby number kind of regime. Whereas your turbulent contribution is acting, of course, like a high Rossby number. And so what's a little puzzling to me about this, though, is that you do appear to have banana cells in your movie. And so is it, the way you tend to get this kind of pattern on the right from the flow, as opposed to the magnetic field, is when those banana cells sort of tilt in the prograde direction. Is that not happening in your models? Are they just rounder and not tilted? I'm a little puzzled by this since you clearly have them.
Yeah, actually, so I haven't seen the equatorial plane, and I haven't seen the tilted banana cell. But actually, so when we see the movie, we can see some evidence of the banana cell. But we also have the very small scale turbines. Maybe so this contribution is very large, and as a total, maybe the convection stays in the high Rossby number.
Okay. All right. I have more questions, but I'll pass on to Lauren now, and then Irina.
Okay, thanks, Hideyuki. I have to change. My topic of discussion was why don't global models reproduce near surface shear, and I have to amend that to say why don't global models, except for yours, reproduce near surface shear. No, it looks really interesting. My question, it probably goes back to your earlier work with and again on this figure, slide 17. The magnetic field seems like it's taking the place of the banana cells effectively in transporting angular momentum outward. Why, for the Bussy columns or banana cells, they have a preferential tilt, and there's kind of a cartoon way to understand that angular momentum transport. Is there something similar for the magnetic field? Is it tilted somehow to make that preferred correlation, or what's going on?
Okay. So some magnetic fields want to be parallel to the flow. So in the high Rossby number regime, so BR B5 should be negative. Okay. And the magnetic field also want to be tilted like this. So the BR B5 also negative. So this can transpose the angular momentum radially outward. So this is why. So this is a very okay. Sorry. So this is a mistake. This is a plus sign, and so there is a minus sign and a plus sign. So if the correlation has the same sign, the angular momentum transport is the opposite direction between velocity and the magnetic field. So this is the reason. Okay.
Okay, that's interesting. So it seems like in the models where the magnetic field really destroys the differential rotation by kind of being opposite to the Reynolds stress, it can actually help you in the case where the Reynolds stress would have made you anti-solar. Is that, I think that's might be, okay, that's interesting.
Okay, thank you.
Irina?
Yeah, thank you. Thank you for talk. If it is possible, can you go to previous slide? Yeah, yeah. I'm a bit confused with these plots, and looks like you include probably. My origin of confusion is values for RMS velocities, and on such deep layers like 0.9 depths, it is already 100 meters per second. Of course, for deeper, a little bit less, but it seems for me it's so strong flows you have on such deep layers. Can you comment this?
But I think this is a typical value for the global calculation. Of course, it depends on the resolution and the magnetic field, but this is a acceptable range, I guess. So in the deep, in the base of the convention zone, this is a 15 meter per sec, and the 0.9 around the 100 meter per sec. So I think this is a bit slower than the typical calculation.
Yeah, those seem like reasonable numbers to me as well. It's pretty typical for global models.
Yeah, but then the flux transport will be much higher than a solar model. So what is the luminosity in your model?
Luminosity is a solar luminosity.
Even with such high convective velocities?
Yeah, yeah. So I can show you. Oh, wait a minute. I guess I have the sorry, I don't have it, but actually, so
it's okay.
My luminosity is a solar luminosity. Yeah.
But previously you showed different simulations with low luminosity, because you show many cases. It is very hard to follow which case you discuss in each time. So,
this
what
one
difference
is solar
with the
luminosity.
low luminosity case?
So low luminosity case is my previous calculation, and this new calculation is I just use all the parameters solar parameter except for the diffusivities. Okay.
Okay, and just I want to ask you more, a little bit maybe more discussional question, but maybe I misheard you, but you said angular momentum in your simulations transported just by magnetic field. And can you explain this more, if it is possible?
Okay, so maybe I guess this one. Okay, so okay, wait a moment. So magnetic, angular momentum. Okay, angular momentum can be transported by Reynolds stress or Maxwell stress or meridional flow. So the so the correlation between when maybe so it takes very long time to explain. So it takes typically several hours. So
okay, maybe I refine my question. My confusion is we have such configuration of magnetic field like when we discuss about solar activity because of solar rotation. But when you have a stronger magnetic field, especially your claim what you have over partition magnetic field in very deep interiors. So it means you efficiently suppress rotation and turbulence. So it means it I don't see a reason how magnetic field can be transported to any place. Maybe
so,
except only using only due to diffusion only. Maybe.
Okay. So important point is the magnetic field transports the angular momentum, and this can cause the meridional flow. And the axial player is a meridional flow. So that this can generate the differential rotation. So when we just analyze for example, B theta B phi, this want to suppress the differential rotation. The final state, the angular momentum transport by the meridional flow, and the B theta B phi suppression is balanced. So this is a really complicated thing. Okay. Anyway, so please see this paper. This is a 30-page paper, but everything written in this paper. Okay.
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 I think Paul was next, and then Nick, and then David.
Hi. Thanks. Thank you for a very interesting talk. I am a little bit confused by your comparison of travel times, which you estimated with Gizon et al. Result. But I thought Gizon et al. Travel time, they say it is consistent with a deep return flow, which is single cell return flow. But I thought your figures for meridional flow is very shallow, I thought. So I'm just wondering what you mean by the consistency here.
Okay. So yeah, so they did an inversion. So this cap maybe so you are good at the helioseismology more than me. But so they depend. So they also include the error bar in the deep convection zone. So in their paper they said that due to the very large error bar in the deep convection zone, this data is not used in their inversion. So the inversion result and our calculation result can be changed. So we just want to compare with the travel time. So the travel time is a more direct observational result. So the inversion result depends on their assumption and their out of sync. So this is my answer. So the inversion result depends on the assumption.
Okay, thank you.
Okay.
Yeah. Thanks.
Hi, I congratulate you on a heroic calculation you've done here, first of all. Secondly, I just want to ask, I mean, a lot of this hinges on the fact that you have this super equipartition magnetic field in the deeper convection zone. But this is pretty unusual for dynamos to have a super equipartition like that. Or is this becoming common at very high Reynolds number global calculations now? Can anyone sort of comment on this?
So actually, so we analyzed our previous calculation and we found that the super equipartition magnetic field is maintained by the compression. So this indicates that we can use the internal energy to amplify the magnetic energy. So in the deep convection zone, internal energy is 1 million times larger than the kinetic energy. So when we can use only the very tiny fraction of the internal energy, the magnetic field can be a super equipartition than the kinetic energy. So this is the reason why we have the super equipartition magnetic field in the deep convection zone. The reason is due to the low Mach number.
Okay, and the fact that you have a lot of density scale heights.
Yeah.
Interesting. Okay, great. I'll look
On the note of the super equipartition magnetic fields, though, so I'm assuming your magnetic Prandtl number is approximately 1 in this kind of formulation, whereas it should be quite a bit smaller than 1 in the actual sun, right? And so do you feel, feels a bad word, but do you think that this compression effect will kind of outperform the enhanced diffusion of the magnetic field that you might expect in the actual system? I guess it's a question of time scales and spatial sizes, like for the downflows.
Yeah, so possibly, but important point is of course the magnetic Prandtl number is very small in the solar convection zone, but at the same time, magnetic Reynolds number and the Ford Reynolds number is much larger than our calculation. So we think that we don't overestimate the diffusion. We should overestimate the diffusion. So important point is the magnetic diffusivity and the viscosity is always larger than the reality, and then the Prandtl number is smaller than 1. So actually, so the Prandtl number issue is very important, but I don't know the ultimate answer for the magnetic Prandtl number issue in our result.
Okay, thanks. I'll move on to David. That was related to Nick's questions.
All right. First of all, fascinating work and very well presented. Thank you so much. It's clear that the magnetic field is critically important in this. So I have to wonder, given the changes in the sun's global field over a solar cycle, what does that do to the flows as those fields change? Have you thought about that?
So actually, unfortunately, we haven't reproduced a large scale magnetic field pattern. It's like the solar cycle. But we expect that the magnetic energy in the convection zone is very, very large. This is much larger than the large scale magnetic energy. So currently, I don't think the magnetic fields associated with the solar cycle is not very much important for the large scale flow. Of course, large scale flow is important for the large scale magnetic generation, but maybe large scale magnetic field is not very much important for the large scale flow generation. This is my current feeling, but maybe wrong.
All right, thank you.
Do your models cycle at all? Do they have any kind of magnetic cycle?
Currently, no.
No, I mean, it's interesting, right? Because most of the models over the past 10 or 15 years that have shown cycles are very low Rossby number models. If you're measuring the flow speed after the fact and computing a Rossby number, it's around, I think usually around 0.1 or 0.03 or something. I don't know. I looked at this at one point. And what's the Rossby number in this system if you take some kind of bulk average?
So Rossby number is difficult number, but for example, I show this one. Okay, so I show, in the previous calculation, this is almost identical to my current one. Where is it? Okay, here. So there are several Rossby numbers, so convective Rossby number and the Rossby number and the local Rossby number, something like that. So you should see this here. Rossby number is 1.25. I guess no, 0.12.
Okay, so even as so while your flow is still giving you a high Rossby number Reynolds stress, the Rossby number is going down due to the increased resolution and the stronger, more compressed magnetic field. Okay.
Yeah. Okay.
Did someone else have a question? I thought I saw a hand up. I think Irina.
Yeah, I have a very quick question regarding sound speed treatment. I understand you face a problem with numerical cost. It is fully understandable. But my concern how such treatment affect results. Have you tried to reduce effect of sound speed reduction to at least check how it affects your results?
Okay, thank you for the question. So for this new calculation, I haven't checked, but in the previous high resolution calculation, we have checked. And there's almost no influence from the reduced speed of sound treatment. But one possible influence can be thought is that so we found that the super equipartition magnetic field is generated by the compression. So when we reduce the speed of sound, so this compression decreases. So we can underestimate the strength of the magnetic field in our reduced speed of sound technique. So this can be checked with an anelastic approximation. So in the anelastic approximation, the speed of sound is infinite, and we can compare the result with the anelastic approximation. But anyway, so currently, we haven't seen any influence for the generation, even generation for the magnetic field. Okay.
Okay. Any other questions for Hideyuki? Cool. Thank you for a very nice presentation.
Thank you.
And I think we'll move on to the next bit of the discussion. Rudy, do you have an idea of where we should pick up with the discussion? Maybe we should see who actually has some slides they wanted to show. We've kind of
Yeah, I
Yeah,
think
can-
it might be easier to ask who had of this still the discussion sessions that are still outstanding, who has anything prepared, right?
I have prepared a few slides actually. So
Okay.
yeah, so this is Vibhuti.
Okay.
So do we want to take a quick break, or do we just keep going? What's the general consensus? Any preference?
Yeah, I am okay with.
I prefer to keep going, but if people need breaks, I totally can relate to that.
So I think if there's no contradiction, and if you're ready to go, how about you go?
Okay. So I will share my screen. Yeah, so can you see my screen?
Yeah.
Yep.
Okay.
Yep,
Okay.
that's good.
Yeah. So this work is a detailed work that is published in MNRAS. So let me briefly tell you about myself. I am Vibhuti, just completed my PhD, still haven't received my degree from the university, still waiting for that. So this work was a part of my PhD thesis work. And so most of my work was related to the observation, but in this work, I have worked on the theoretical model of near surface shear layer. So from the beginning, we have all discussed about, so I don't have to go to the what are the near surface shear layer and even the thermal wind balance equation. So I will start with the very basic idea about the thermal wind balance equation we all are familiar with. So here you can see the one term that we call centrifugal term, which try to drive the plasma in this from the equator to the pole. So idea is that since this JAD is the axis parallel to the rotation axis, and since sun is rotating differentially, we will have the different centrifugal force at these 2 points, and that will lead to the rotation, and it will drive the plasma in the equator, like from equator to the pole. But there is another term that is we call as a thermal wind term. So if we assume that for a time being that if pole is slightly hotter than the equator, then it will drive the thermal wind term that will be in the opposite direction. So now if the meridian, there is another term along with these two, but our idea is that that term will be very less, because the order of magnitude calculations show that that term is actually very low compared to these two terms. So that definitely means that these two terms are balanced, and the slight difference in the centrifugal term that is actually leading to the observed meridional circulation. And another thing that I would like to point out here is that only one of them cannot drive the meridional circulation, because the magnitude of these terms are very high, and whatever we have observed from the observation, we know that that is not in the agreement with the observation. So definitely both of the terms are playing very important role to drive the meridional circulation. And our idea is that this equation is also valid in the upper layer of the convection zone. And earlier the belief was that this is only valid in the deeper layer, and it is invalid near the surface, and it is not valid near the surface, and that leads to actually the near surface shear layer. But our idea is like opposite to that, that this equation is still valid near the surface, and it can actually lead to the near surface shear layer. So to understand that, there are some assumption that we're assuming the ideal gas, we can write the entropy term like this. And there is another term that we are assuming is that, so we have the standard model, and here we will be using the solar S model by Christian Dalsgaard. So our idea is that we know the temperature profile of the sun, that is 1D model, and because the convection zone is convection is not included in that, like rotation is not included in that. So what will happen is that the temperature profile we have that is valid along the rotation axis. So what we are doing is that, like since rotation will try to affect the convective cells, and the convective cells that is moving along the equator, like along the rotation axis, that will be least affected by the Coriolis force, and the one that is moving along the equatorial plane that will be mostly affected. So if that is the case, that will introduce some latitudinal dependency in the temperature. So if that is the case, we can write the temperature term like one term, that is whatever temperature is near the pole, and plus some additional delta T r theta term that will depend on the latitude. So if you consider these two, that will lead us to this equation. Now let's try to understand why we think that this equation can lead to the near surface shear layer. So we already have discussed, like there are a lot of discussion about convection is least affected because of Coriolis force in the upper layer of the convection zone. So our assumption is that there will be some transition region, suppose for example R equal to RC. So for R greater than R equal to RC, the Rossby number is very large and Coriolis force will not affect the convection. And the Rossby number is low in the deeper convection zone and it will be affected. So if that is the case, whatever temperature profile we will get at delta T profile we get at R equal to RC, that will remain same. So that means delta T will become independent of R. So this equation will be valid. Delta T will be for R greater than RC will be exactly the same whatever we get at delta T R equal to RC. Now, based on this, if this term is not changing much, so and now we know that from the temperature profile of the sun, the T is decreasing very sharply near the surface. Now, if that happens, the combined effect of these two effects, like temperature is decreasing very rapidly, and as well as this term is almost constant. So this will increase the thermal wind term. Now to balance that thermal wind term, so another term, the centrifugal term, will also have to increase. And our idea is that that will lead to the near surface shear layer. So let's see that. So, okay, let me go back to the previous slide. And how are we going to solve this equation? That is the important part. So our idea is that since we have known omega from the helioseismologic observation, so what we can do is that we can solve this equation for delta T in this region. And whatever delta T we will get at R equal to RC, we'll use that delta T profile to calculate the omega in the upper region. So like for R greater than RC. And based on this, we will see, like, are we able to produce the observed NSSL or not? So first thing that we have done is that we have calculated the delta T, but right now we don't have any information about the RC, what will be the value of RC. So we calculated the delta T, and here you can see the delta. We don't have the helioseismic observation with high certainty in this region. So that's why we have restricted ourselves only up to 70 degree in latitude. And you see this is the temperature delta T profile from calculated for 0.7 to 0.98. That is the region we are expecting the NSSL. And based on observation, we know that it's something around 0.96. So then what we have done is that we have assumed the different value of RC. So for example, here RC equal to 0.93. And this dotted line is representing the RC value. And here, what we have done is that we have calculated the delta T at RC equal to 0.93 and used that in the thermal wind balance equation to calculate omega in the upper layer. So here the two curve, one is representing based on our model, and the red one is representing the contour from the helioseismological observation. So what we have done is that we have changed the RC value for 0.94, 0.95 different RC value. And based on the visual estimation, we can say that RC 0.95 and 0.96, 97, these are looking matching well with the observation. But and 0.98 we have rejected because based on observation, we see that the 0.98 is not the candidate for the RC value based on the observation. So based on this, we can say that RC is matching well, but again, we have looked for the error estimation for this case, all these three cases. And we compared the observed value based on helioseismology, and we see that the 0.96 giving us the error of around 1.3% RMS. And you can see here the distribution of error in all these cases. And at radii 1, the error is large, and we believe that this thermal wind balance equation breaks down, and that's the reason our error is pretty large, exactly near the surface. But in the deeper region below that, our thermal wind balance equation is able to produce the observed NSSL. Apart from that, we have also looked at the temperature delta T, pole equator temperature difference for our RC value, and we see that at 0.96, the value is around 2.5 Kelvin, and that is actually in the agreement with the Rast et al. Work in 2008. So they have used the Mauna Loa data, like PS PD data from Mauna Loa, and estimated the pole equator temperature difference. Here they have also the pole equator temperature difference. They have mentioning the pole around 70 degrees. So difference is only like it is same in both these cases, and these two are in agreement. So now that is our conclusion that the thermal wind balance equation, this very simple equation, can lead to the observed NSSL. So that's it. Now, very briefly, I have explained this. Now it's open for the questions and the discussion. So I'll be happy to answer if you have any questions.
Great. Well, thank you. Thank you very much. So do we have questions from anyone in the audience?
Everyone is tired now, I guess.
Looks like somebody's trying to connect to audio. Just one moment. Or maybe not.
So how does this balance relate or not to what was just presented from a more simulation kind of point of view?
Yeah, so that has not been verified. And another point here is that RC value, that we have a strict boundary in our model. So we are expecting that in the simulation, we will not have that strict boundary in real sun. So for the simplicity, we have assumed this RC as a strict boundary, but definitely, but again, yeah, so we have to look into the simulation and compare that how it is in agreement with the simulation works.
And just one more quick question. I see Nick has a question now, but and maybe I missed it, but what is sort of the expected strength of the centrifugal force relative to the Coriolis force in the near the photosphere where we can measure supergranulation? Is it substantial?
So I have not estimated it, but the order centrifugal force is of the order of 10 to the power minus like this term, not the centrifugal force, this term that we have in the left hand side. So that term is of the order of 10 to the power minus 12. So there is one work by Arnav Rai Chaudhary. Actually, in this work we have substantiated that work. So in that work they have order of magnitude calculation of all these. So all these different terms and what are their contribution. So he has also discussed about the dissipative term. So there is another dissipative term along in the thermal wind balance, like in this equation, and what are the effect of that. So, but the order of magnitude calculation, so that will be like around 10 to the power 4 order of magnitude less than the thermal wind term. So that is not responsible for, that cannot be responsible for the near surface shear layer.
Okay. Let's see, now we've got questions from Nick and Paul.
Mine was just a comment on that, actually. I mean, isn't it almost, I mean, maybe I'm misunderstanding something, but it seems to me like this idea of thermal wind balance and what Hideyuki presented are almost diametrically opposite, right? One relies entirely on Reynolds stresses and Maxwell stresses, and this one doesn't. Is that not correct interpretation? Or am I missing something?
Actually, I didn't get your question very properly.
No, there wasn't a question. It was a comment. Is that your theory here, wind balance is almost diametrically opposite to what Hideyuki was presenting. His relies entirely on Reynolds stresses and Maxwell stresses, right? You have no Reynolds stresses and Maxwell stresses.
Yes. Yeah.
So very interesting question as to which of these.
It's a completely like whatever was the earlier idea in working on this model, that is completely opposite of the earlier understanding of the how thermal wind balance, how NSSL will arise. So it's a completely opposite idea that we have given. But yes, because of the observational support from the Rast et al. Work that the pole equator temperature difference of around 2.5 Kelvin, how it can, and along with the fall in temperature in the upper layer of the solar convection zone, can lead to the near surface shear layer.
Okay, go to Paul, and then I see Irina has a question after him.
Hi, Vibhuti. Thank you.
Hi.
Thank you for being awake so late in the night for you there. Yeah, very interesting work. So you have a prediction for the pole equator temperature difference.
Yes.
So
yes.
in this situation, if you want to drive a meridional flow poleward, you should be able to estimate the centrifugal force term, right? I mean,
Yes.
is there an estimate of that term compared to the thermal term to drive the meridional flow which is observed?
Yeah, so we have assumed that the thermal, like the meridional circulation is steady, and that is based on that only this two equate. And there is another term that our idea is that the another term that is dissipative term. So if there is a negative term here, so then these two are the difference between these two terms. So in the centrifugal term and thermal wind term. So that difference will lead to that small observed meridional circulation.
Okay, so that has been verified from this.
Yeah.
Okay.
Yeah.
Okay, thanks. Yeah.
Irina?
Okay. Okay, hi. Thank you for this presentation. My question is not 100% relevant to your talk, actually. It's mostly to discussion because I'm curious when I hear presentations about wind balance. Of course, it's very interesting effect, and I always start thinking about physical reason for this. And I don't know if you can answer on this question. Maybe somebody who listening this presentation can comment on this, because yeah.
So like physical interpretation that
I mean, why we have this gradient in temperature?
Okay, so the idea is that like because we know that in the convection zone, like definitely it is called convection because the heat is transferred via convection. So when plasma blobs or convective cells are moving along the rotation axis, the effect of Coriolis force will be 0. And when it is moving along the equatorial plane, it will have the maximum effect. So the effect, if it is affected by the Coriolis force, the heat transfer will be affected. And that's the reason we expect that the pole will be slightly hotter than the equator. And if that is the case, along with the fall in temperature in the near the surface, so that is idea why we are expecting the pole will be slightly hotter than the equator. But yes, again, it is very like tricky to measure that pole equator, even though the Rast et al. Has estimated the difference. But yes, again, the difference is around 2.5 Kelvin, and that is very tricky to measure that difference in temperature.
The other thing I just want to mention is that the giant cells or boosted columns, if they do exist, my work suggests that they transport heat poleward directly, so that they actually have a correlation that heats the pole.
Yeah.
Okay. Yeah, interesting. Yeah, thank you.
Okay, well, thank you. And I'm curious, was there anyone else who had some slides or thoughts that they wanted to share?
I did, but we kind of got to it all with Hideyuki's talk, because it was about why don't global models reproduce near surface shear. So I don't know how relevant that is at this point.
It seems to me to be relevant.
Yeah,
actually.
yeah.
All right, let me, all right.
I'd like to see that too. Yeah.
Sure, I just have 2 slides, so it'll be quick. 1 sec. Do you guys see am I in presenter mode?
No, it's PowerPoint mode.
No. Okay, hold on. What about now?
You look
Yeah.
correct. Yeah.
All good.
I don't know if I'm okay. Do you see all your faces too?
No, we just see your slide
okay.
all by itself, nothing else.
Great. All right. Well, my question kind of goes back to before Hotta 2022, Hotta et al. 2015, and then my work, Matilsky et al. 2019. Basically, we have the near surface shear layer on the left that for a long time was believed to arise essentially due to the Rossby number transition. So rotationally unconstrained fluid near the outer surface would homogenize angular momentum, leading to this negative radial gradient of the rotation rate. And one reason that might be the case in the sun, probably the main reason, is the density stratification. The fluid is in the sun about 1 million times less dense than from the bottom of the convection zone. And so the idea of the simulations was kind of to push at that limit. We can't do 1 million in density contrast, but we can get up to a few hundred, now a bit more probably. So Hotta did 600, I did 150, and we basically found that there was not that much near surface shear. So there were some effects of near surface shear. The contours did something a little bit near the surface that looks like a shear layer. In my work, the contours look like they're a little bit more bent than they really are. Their overall rotation rate is very weak in the polar regions on the right. So it's still really not a near surface shear layer. And like Hideyuki mentioned, it doesn't do very well in terms of the contours at mid latitudes. And I guess my question that I want to pose is why? Because the simulation is doing the right thing. I mean, it's following the theoretical idea that there's a Rossby number transition and rotationally unconstrained fluid is homogenizing things near the outer surface. And I mean, I propose, and I think this applies to both Hotta et al. 2015 and then Matilsky et al. 2019. Basically, we have this small scale mixing. So this is creating a negative torque from the Reynolds stress, which if it was unopposed should create a near surface shear layer. And then in both of our works, there was also a thin band of meridional circulation that opposed it. And it was thinner than should be suspected from helioseismology. So one of the more recent helioseismic results is shown on the right concerning the meridional circulation, and the thickness of that poleward flow is pretty thick. It's like 10% the solar radius, whereas the simulations are getting a few percent the solar radius. And so I'd argue that in the simulations, it seems that the meridional circulation is doing whatever it can do to eliminate the shear. And it's also being unphysical. So we have a thin band of near surface Reynolds stress, and the meridional circulation is responding by occupying a thin band. It seems like all it wants to do is eliminate near surface shear. And also that band is not what we'd expect from the sun. And furthermore, if there was Reynolds stress in the sun making the near surface shear layer, that would occupy the outer roughly 5% of the sun. And clearly the meridional circulation is not just occupying the near surface shear layer. So I guess my question is why? Why is the meridional circulation doing this? If I don't know if Hideyuki is still here, but if I don't know what the meridional circulation looked like in his case, maybe it's doing something different. Maybe the problem is eliminated when we put in magnetic field. But that's basically it. Why the models try to create near surface shear and then they're inhibited by the meridional circulation. And I don't have a good answer for why that would happen.
I don't understand. So you expect that if you have this shear at the top, you expect having meridional circulation, right? And this is, what is the meridional circulation that you get, Doran?
Well, it's like a 2-cell, yeah, I should have put the actual meridional flow. Well, it looks like Hotta et al. 2015. So lower left, that's actually the poleward flow. So you have poleward flow in a thin band. Mine does the same thing, but it's a bit thinner. But yeah, the thickness of that band is a few percent in the simulations, which seems to just occupy, like, be whatever it has to be to kind of eliminate the near surface shear, because the Reynolds stress is transporting angular momentum in, and then the meridional circulation is directly opposing that.
So this is correct, right? So that's what you expect, and you don't expect to have an unbalanced state, because if it is unbalanced, then you will have a loss of angular momentum, or you will be gaining angular momentum. So you expect to be balanced, and the motions arrive from the fluctuations over this balance. And what I understand from the recent paper is that the fluctuations can be very quickly wiped out if you have a strong viscosity. If the viscosity is too large, compatible with the turbulent viscosity, then the fluctuations that will sustain the motion, they are very small, and then you don't get this. You get a balance, but not a sustained flow.
Sorry, so you're saying when the viscosity is?
I am saying that the motions are sustained because of this balance, or these terms have fluctuations over. These are in statistically steady state, right?
Yeah, that's
so.
Right.
If you have this negative transfer of angular momentum because of the Reynolds stresses, that's what you are having, right?
Yes. Yeah.
It is balanced by the meridional circulation, and that's fine. That's what you need to have. But your fluctuations are too small to sustain the loss of angular momentum, or the near surface shear layer, or the shear at this point. That's my idea. And a way to test is to decrease the viscosity, for example, in this very simulation, and see what happens.
Right. Oh, because you're saying that because of the viscosity is too high, then that's going to eliminate any fluctuation fairly rapidly.
Not any, but they will last less time than they should be.
Right. Okay.
That's an idea.
Yeah. Okay. I'm still wondering, why do we expect this inertial balance? So if we,
because we have to conserve angular momentum.
Right, but I guess the issue, and maybe this goes back to your thing about viscosity, is there's another way that this could happen. I mean, my viscous stresses are very small. I think that was the same in Hotta et al. 2015. So if the system could respond by establishing a near surface shear layer that was with the viscosity balancing things. It seems like it could be easier if the viscosity is high in this case, just because that could provide a stronger balance. But I mean, why is the balance just between the two inertial terms with the viscosity not playing a role? I guess that's because that's the other. It might be just particular to these two simulations. I don't know.
Mm-hmm. So the scale of your viscosity is the same of the scales of the meridional circulation and Reynolds stresses. Is that correct?
Yeah,
I mean
in terms of the torque, I mean at low latitude. So for example, deeper down, you can see that the viscous torque is actually
right.
Quite
But it could be if you reduce the levels, change the levels to half of it, and then you probably will see some viscosity there.
Right.
I'm not sure, but it could be still the same order of magnitude.
Right. Okay. Yeah. Yeah. Okay.
This is that way. Of course, this is just an idea. I'm not saying that it's gonna work, but it could.
Right. Okay. I don't know if are there hands up from before, or is that?
No, I think those are new.
Sasha has hands up and Irina has a hand up. So
right.
Yeah, actually, I have some kind of a long comment. Maybe first you and Irina ask questions.
Okay, I have just a quick short one, a clarifying question with regard to the density stratification. When you say the models have sort of like 2 orders of magnitude and the sun has 10 to the 6, the only thing that I know about density is the model S from JCD, right? And so the density varies mostly near the surface. So it's really just not much happens in the bulk of the convection zone, and all the drop in density happens very close to the surface. I mean, the outdoor 1-2% is where it happens. Is that sort of reflected in the models, or would that matter? Just a question. I do not know.
I think we hope it doesn't matter, because I mean we can't simulate that far, but
so yeah, Rudy, if you kind of go like a megameter in, so you're thinking you're sort of below the base of granulation, you've got something like 11 e-foldings in density. And so to some extent, that might be what you want to capture if you're not actually trying to go all the way to the photosphere.
Mm-hmm. Yeah, I guess my question was, since the near surface shear layer is sort of the outer 5%, so, and lots of the density variation really happens in that regime. So that's why I was wondering if that matters, or
it probably does.
What the thinking is.
Can I say something? So we previously characterized our calculation covering whole convection zone from base to the photosphere. Now we compare the result with photosphere and without photosphere. And but at that calculation, so we didn't cover the whole sphere, and no rotation and no magnetic field. But in that calculation, so we haven't seen any difference between deep convection structure. So currently, we think that the photosphere has a very minor role in the deep convection zone structure. My current understanding something like that.
So was this with the full stratification? So basically 10 to the 6. Oh, wow.
Yes.
Okay.
Yeah. Let's please see. I will put the link in the Slack.
Okay.
Yeah, I would like just it not really. I cannot unfortunately help with answer on this question. I will love to solve this problem, but again, it even comparison with your simulations, it kind of too tricky. Just at one point on your sphere, right? Essentially, but I really like this question, and when I start look such examples of two models, global models, what I notice, I actually try zoom both models, and I notice some decrease in velocities as you go to upper boundary. And of course, we know for global models, it is upper boundary located somewhere below photosphere. But my question is it possible what we have problem with formulation of boundary conditions because you know flows near boundary is always tricky. So, and I just start thinking what because say it boundary conditions probably didn't allow to penetrate flows through boundary. It create kind of like artificial suppression of flows. It's why we are getting flows near zero, and it essentially affect on large scale pattern below just because of this. What is your opinion?
Yeah, I mean, I think if most of us have an impenetrable, I think all of us, impenetrable boundary at the top, which is totally not physical. I mean, it would be like going into the sun and just putting like a metal shell around everything, and all the fluid coming up just goes splat. As far as how, well, there's a few things going on. There's the boundary that's impenetrable. There's the fact that we don't have the correct small scale physics. We don't have radiation or ionization. I think the real issue is that we're not capturing, again, the smallest turbulent scale. So things on the sun are getting driven at a granular scale, more or less, and even scales smaller than that if you include a cascade. And we're just beginning to get scales of like a few megameters in the global models, which is still significantly bigger than granulation. And how that affects like angular momentum transport, I mean, I think that's an open question. So that could be relevant because that would mean that this, essentially, when we talk about viscosity, we're saying that there's a turbulent viscosity, but it's not, it's hiding whatever the small scales are doing. And so, yeah, I think the boundary conditions could play a large role.
I just wondering, oh, sorry.
Yeah.
I just wondering if it is possible to put kind of buffer layer. Of course, it will be in any way unrealistic, but it will allow flows kind of interact in some more physical way. Of course, such buffer layer in any way unrealistic, but it probably will help such flows, what you pointed on your slide, behave more realistic and actually accelerate and be stronger. Or, I don't know, just guessing it.
Yeah, I think actually a long time ago, Sasha Brun from Saclay mentioned something like this, where you put a small super adiabatic layer at the top, and so upflows get decelerated, and then you effectively don't have an impenetrable condition. But yeah, I'm not sure how that might get tricky too, because then you're going to have to still get heat out of there, and so you're going to have to put like a cooling layer somewhere, and you have to have some boundary condition at the top of that super adiabatic layer. So it might be tricky, but yeah, it'd be interesting to do something like that.
It is worth noting that the impenetrable boundary condition isn't completely crazy. You know, you've got what we all presume is a low Mach number flow that's trying to pass through several density scale heights on the way toward the photosphere. And so there has to naturally be a lot of overturning of the fluid anyway.
Right.
And there's some paper, I think Jesse Lord is the lead author. He was something he did with Mark Grass, maybe Ake Norland was on there. This is back from like 2014 or somewhere in there. And they actually talk about this kind of overturning effect for different reasons, but it sort of naturally arises from the fact that you have such a strong density stratification anyway.
Right. Okay. Yeah.
I think we're ready for Sasha's long comment.
Yeah, so I have actually prepared some slides and for discussion topic. So I wanted to skip it because everybody tired, but I think it's relevant to this discussion. So Lauren, if you can, I want to show you screen. So this was the topic I suggested, special scales and time variations of solar subsurface convection. I'll show some observational results that kind of surprising that we recently got from by time distance helioseismology analyzing time distance data. So in time distance, you actually get a very detailed flow maps. So you can see that some just a small portion of solar surface, one of synoptic maps that's wave producing. And you see supergranulation pretty well here. So wondering how deep the supergranulation is, if you can, and these flow maps and what the spectrum of these flows. So we calculated divergence, horizontal divergence at different depths. And you can see divergence flow maps. And you can see kind of structure changes with depth. So we took, we don't have data in polar regions, but we took in our analysis of polar regions and we calculated power spectrum. So we did composition to spherical harmonics. This is just for some period of time, but this is for the whole HMI observations and studies with solar cycles. So what's interesting here on these diagrams, you can see the spectrum as a function of spherical degree L and horizontal axis and azimuthal number m in the vertical axis. And here you can see that this shows at 0.5 at megameters below surface, 2 megameters, 4 megameters, 6, 8, 11, and then 15 and 19. And what's interesting, this first you can see at around 100 is the supergranulation, the enhancement of this divergence spectrum. And then at the depth of below 5 megameters, it suddenly changes. It changes to 50 megameters and then gets quickly displayed to even lower L. So then it gets to the scales what Dave Hathaway here argued that some giant cell scale. And this happens quite shallow at a depth of 15 megameters. Here, maybe wondering how resolution affects this. We also studied that resolution averaging kernels, and actually we identified that with observational noises. So it's we believe that these are relatively clean measurements of the spectrum. But the point here is that we can see some that what kind of what Laurent said, that this kind of a shallow layer that is different from the deeper layers. And this probably relates to the spectrum of convection. So that's something we need to look carefully. And in fact, it's not change here that from supergranulation to larger scales, the scales overlap at these depths. So it depends on how we calculate that. First, we calculate the some power harmonics per single harmonic. You divide the spectrum, sum of the over m at single L, or you can take power of all L's. And here it's a different curves here. The dash curves, it's a total power, and solid curves, you can see there's more displacement towards the low L. So this, I think, it's what maybe that's something relevant to. And as we know that supergranulation has not been reproduced by any simulations. And also we look at the solar cycle variations. It also was quite interesting. So on the left, you can see some peaks at annual variations, and we clean this with some filter annual variations. And what we found that at shallow depths, the power, station power anti-correlates with the sunspot number. But below 5 megameters, we can see the positive correlation. So what that means in terms of that modeling, that probably that at least this kind of superposition of supergranulation scales at much larger scale at very shallow depths, something that probably should be reproduced by simulations. Okay, thank you. That's all my comment.
Let's see, Irina's got a question or a comment.
Yeah, I have a question. maybe you, Sasha, run too fast with your slides, so I try
Yeah,
to
but we're
capture as much
already
as I
1
can.
minute late. Yeah.
Yeah. So my question is, according to your first, I believe, first slide, when you demonstrated enhancement power for different L with different depths, it looks like supergranules are quite shallow, much more shallow than it is previously expected. I'm right, or it just I'm not sure if it is correct to say like this.
Actually, that it's they're shallow, but we can still see in terms of the total power, it's still on supergranulation scale. It's still, if you look at the power per mode, then it's the solid curves here, and dotted curve shows the uncertainties in these calculations. And say if you look at the 15 megameters, we still see the supergranulation power. We still see it. And but you know that if per unit mode, in the total power, but per unit mode, it's displaced towards low L. It's like L10, so it's a range of giant cells that Hathaway and Lisa, they found this also on the surface convection by making that tracking supergranulation.
Just to clarify, the clarification, it is during overhaul cycle, or you select. I'm wondering if you can select magnetic effects.
Right, yeah. So magnetic field, I forgot to tell this. Yeah, we actually mask magnetic field. We did without masking, and then we use magnetograms, synoptic maps, and mask strong field greater than 100 Gauss and 200 Gauss to check, you know, how magnetic field affects this spectrum. So it's a relatively small change in this when we mask magnetic field.
I have also a question. It is kind of, I had such question in previous our discussions regarding masking of magnetic field. I think masking, my problem with the masking of magnetic field is, yes, we observe some magnetic field on solar surface, but usually as we discuss about subsurface layers, usually magnetic field I expect will occupy a much larger area. And it is kind of probably very tricky to figure out. We don't know what distribution
No,
of
it's obviously
magnetic
effect of
flux
magnetic
is.
field on convection. That's what I showed in this slide. You know, this effect with solar cycle. It's the effect of that what we think it's a large scale magnetic field, and that it's probably that what it affects the anti-correlation at the shallow subsurface layer, and then correlation with magnetic field in deeper layers. So it obviously magnetic field changes the structure of convection. That's for sure. And how it affects the surface shell layer. We also saw that Rudy showed some effects of the solar cycle. So some deeper layers are obviously affected by magnetic field. Maybe not directly magnetic field, that what some models, mean field models showed, it mostly effect of a magnetic field change the flux transport, energy flux transport, and that's an effect. It's not direct of Lorentz force, but it comes through the heat transport.
Yeah, if I comment to Irina's, I think it's a valid point when you try to mask out active regions. As long as you want to create an active region subset, I mean, then it doesn't matter much if you cut it too tight. But if you want a quiet region subset, then you're right. Then of course there might still be a little bit in your field that you include. So you have to be careful how do you do that. So yeah, and of course, if you would know what the magnetic field looks like below the surface, we wouldn't have to do all these kind of things, right? I mean, then we could directly, but yeah. So I just
that's
we all do it as carefully as possible. But yes, we are aware that
but that's why we need that we talk about a lot about this. You know, we need to know numerical models and then compare with observations in order to test all these. So it's I guess that's main direction of the COFFIES project.
Yeah. Yes, it is especially important because when I'm thinking about separation of magnetic field effects, actually on such deep layers like 15 millimeters below, you probably cannot really distinguish individual magnetic structures. It can be like belts, whatever, some large area which start to accumulate at some point magnetic energy in smaller scale. Yeah. Thank you.
No, thank you.
Yeah, and I had a related comment to that is then as you go deeper, then of course your horizontal, I mean, the inversion kernels also vary with depth. They have a profile with depth and also with the horizontal width. And so that is then what Sasha also alluded to in the one thing. You have to be careful that you don't think, oh, everything gets bigger as you go deeper. No, that might just be your inversion kernel, right? I mean, so you have to be careful about these things. And then you run again, as you said, Irina, then the thing is, yeah, if you're depending on how what area or what part in radius that your inversion kernels cover, then yes, you might be you will not be able to tell a flux tube from a flux blob, right? So it's because it's all in the same thing because they have spatial resolution, and so yes, so it's.
I have very quick question, kind of related to your comment, Rudy. As we know, accuracy of local helioseismic inversions decrease dramatically with depth. And the same we can discuss about global when near surface layers usually much not as well resolved. And my question is if you know anybody try to develop kind of hybrid approach to I don't know.
Anybody help us out here? I mean, usually global is global and local is local, but yes, there are different approaches how to incorporate higher degree modes, and that was what and the fitting for that was the writer et al. from this from recently. I forgot, was it this year or a year ago? And they tried to incorporate more high degree modes to push the global results closer to the surface, and that's why the ones you shown. That's why at the 30-degree patch that's where they find then this steep radial gradient. But that is because they push in the fitting procedure to high degree modes. But it's a global method, yes.
Well, we see such a hybrid models, Irina, at AGU at seismology sessions. Seismologists develop this. We don't have, as Rudy says, we don't have manpower for this.
So I encourage seismology group to attend these sessions. I'm not, sorry. It's not my job, fortunately. Okay, thank you.
Oof. I think this was a long day. I think at the beginning, Nick and I, we might have been a bit concerned that we would run out discussion topics.
Yes, that is true. Hey, there's still 24 people on it. 5 o'clock. Well, in Boulder.
Yeah. So I guess if anybody is there who has not spoken and wants to address something, please speak up.
Thanks for organizing this session.
Thanks for coming.
Thanks for coming.
Yeah, it is most productive probably meeting and very interesting. Yeah.
Yeah, it was great.
Yeah.
Great.
Yeah.
I'm about
Thank
to get
you.
out of here. So, guys, we'll see if we can do as well next week.
Oh, you'll do better.
Thanks,
I
everybody.
don't know, if number of attendees that registered as a competition, then you guys won. So far.
No. This is not a competition.
There's a week to go.
This is not mental Olympics.
Well, thank you everyone who contributed. It was nice to hear everyone's thoughts.
Yep.
Thanks. Bye, everyone.
Have a good weekend.
Have a good weekend.
Bye.
You all deserve it.
Thank you. Congratulations. Thank you for the meeting. Bye bye.
Bye bye.